The universe never forgets. Every atom, every photon, every whisper of energy is recorded in the fabric of reality. So when a human mind goes dark, it isn't just a personal ending, it's a cosmic accounting problem. If information can't be destroyed, then where does your consciousness go and what exactly changes in the universe when you die? A heartbeat can be restarted, a body can be cooled, a brain can be shocked back into rhythm, yet something can still be gone. In that narrow gap between reversible and irreversible, physics meets its most human limit. Tonight, we follow the moment of death as a physical event, measurable, lawful, and strangely unfamiliar when you look closely. A flat line is not a single switch in nature, but a cascade. Electrical gradients falter, chemistry drifts, and coordination unravels into heat. And yet, the deeper you go, the less ending behaves like an ending. The brain is a machine made of atoms that obey quantum rules, but it is also a pattern, maintained only by constant energy payment. When that payment stops, what exactly collapses first? The body's order, the mind's unity, or the possibility of a witness? This documentary is not a seance dressed in equations, and it is not a denial dressed in certainty. It is an investigation, guided by what quantum theory and cosmology can actually claim, and restrained by what they cannot. We will separate conservation laws from consolation and mathematical information from the meaning a life carries. We begin at the bedside with the last breath, where medicine draws practical lines that technology keeps redrawing. Irreversible is not a mystical word, it is a statement about what can no longer be restored with the tools available. In the brain, oxygen debt becomes an energy crisis. Membranes lose their gradients, signals desynchronize, and the orchestra that produces a point of view breaks into noise. From there, we step into quantum reality, where superposition and entanglement do not grant miracles but do demand precision. We will confront the myth that a conscious mind is required to make reality choose, and we will watch how ordinary interactions create records that the world cannot easily erase. Decoherence will appear as the quiet engine of classical life, copying fragile phases into the environment until they are effectively unreachable. Then comes the temptation. If quantum effects can matter in living cells, could they matter in thought itself? We will examine what is solid in quantum biology and what remains speculative in claims about a quantum brain. The standard for evidence will be high, because the warm, wet brain is not a laboratory vacuum, and coherence is not a poetic metaphor. To keep the question honest, we pivot from consciousness to something physics defines sharply: information. Not stories, not memories, but correlations between physical states. We will ask what it means for information to be preserved under quantum laws, and why preservation can still look like loss when patterns are scrambled beyond recovery. At the edge of our understanding, black holes wait, cosmic objects that turn bookkeeping into a paradox. We will follow the trail from Hawking's calculation to the modern debate over whether horizons hide, release, or re-encode what falls in. The answer matters not because it promises survival, but because it tests whether the universe keeps its rules even in the darkest places. Along the way, we enter the most controversial territory: many worlds and the seductive idea of quantum immortality. We will treat it as a thought experiment, not a prophecy, and ask what it assumes about identity, probability, and what it would even mean to continue as you. A universe with countless branches may still offer no refuge for a coherent self, and we will approach near-death experiences with empathy and rigor as the brain operates at the edge of failure. We will map what physiology can plausibly generate, tunnels, presences, life reviews, without dismissing the power of what people report. The goal is neither to reduce wonder nor to inflate it, but to locate it where evidence can reach. By the end, our view will widen from a single mind to the long aftermath written into space. Heat leaves as infrared photons, matter returns to cycles of soil and ocean, and faint disturbances travel outward, small, real, and indifferent. Quantum physics will not certify an afterlife, but it will show a universe where endings are transformations, and where what remains is not a verdict, only the next, better question. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across 8 chapters, we move from the clinical last breath to quantum measurement, from neural speculation to cosmic horizons. What you'll find is not a simple answer, but a clearer map of what can persist and what cannot when the self stops running. A monitor chirps, then stutters, then draws a final straight line. The green trace hardens into stillness, and the room's small mechanical sounds suddenly feel too loud. In the bed, a body remains, warm and heavy, but a person is suddenly missing. Clinicians call it a time of death, a line in a chart with a precise minute. Families feel it as a rupture, an absence that arrives all at once. Physics hears it differently, as a change in processes, not a vanishing of substance. At the human scale, death looks like a switch flipped to off, and our language follows that intuition. Breath stops, circulation fails, and the brain's coordinated activity collapses into electrical quiet. The silence feels absolute because our senses track patterns, not particles, and patterns are what make a person recognizable. We notice the end of a voice, not the continued motion of atoms in vocal cords. We feel the loss of a gaze, not the persistence of photons scattering from a face. Pull back far enough and the scene becomes a local event in a vast accounting system. The hospital room is a bright island of order inside a larger world of air currents, microbes and chemical gradients. The atoms in that body were not born in a hospital, or even on Earth, and their story is older than any language for grief. Carbon, oxygen, calcium and iron were forged in stars through nuclear fusion, then scattered by stellar winds and supernova explosions. Over billions of years, dust condensed into planets, oceans formed, and chemistry learned to copy itself. Biology borrowed those atoms briefly, arranged them into cells and memories, and the universe never stopped keeping track. Conservation laws do not pause for grief, and they do not negotiate with meaning. Mass does not evaporate into nothing, and energy does not disappear when hearts stop. Heat leaks into the room, carried by infrared radiation and convection, and the body's temperature begins to drift toward its surroundings. Chemicals diffuse, membranes lose their selective barriers, and molecules begin new reactions that no longer serve a living goal. The ledger changes entries, but the total does not break. This documentary begins here, where the intimate meets the cosmic. We ask what actually happens, not what we wish happened, and we will not pretend that precision removes sorrow. We will stay close to evidence, and we will be explicit about uncertainty, because uncertainty is part of honest science. Mystery is allowed, but claims must earn their place with mechanisms and measurements. If a statement cannot, even in principle, be tested, we will name it as belief rather than physics. The central question is simple to say and hard to face. When a person dies, what changes in the universe's record of energy and information? If a mind goes dark, what exactly is lost and what is merely transformed into other forms? And if physics has limits, limits of measurement, limits of theory, limits of access, where do those limits begin? We need rules before we need answers, because the subject invites wishful shortcuts. First, we separate testable statements from metaphysical beliefs, even when both are emotionally charged. A testable claim predicts measurements that could prove it wrong, and it survives only by surviving that risk. A belief may be meaningful, and it may guide a life, but it lives outside the laboratory's reach. Confusing the two is how people get misled, and how real mysteries get buried under noise. Second, we treat the word quantum with suspicion, not because quantum physics is vague, but because it is exact. Quantum theory is a precise framework with strict mathematics and verified predictions, from semiconductors to lasers to MRI machines. In popular culture, it becomes a magic label for anything mysterious, as if uncertainty were permission. We will not use quantum as a substitute for evidence, or as a shortcut to immortality. If quantum ideas appear here, they will appear with their constraints attached. Third, we respect the human stakes without letting them steer the conclusions. Death is personal, and the room around it is full of stories, but physics is impersonal and often counterintuitive. Our tone can be reverent while our reasoning stays sharp, because reverence is not the same as surrender. The goal is clarity, not comfort, and clarity sometimes arrives like cold air. Still, clarity can also be a kind of respect for what is real. So what is death physically in the medical sense before philosophy enters the frame? It is not a single moment, but a threshold defined by function, and that threshold has changed with technology. Clinically, death is declared when circulation irreversibly stops, or when brain function irreversibly ceases, depending on context and jurisdiction. The key word is irreversible under available interventions, because irreversible is partly a statement about capabilities. A century ago, many arrests were final that today can be reversed, and that historical fact matters. When circulation stops, oxygen delivery collapses, and cells shift into emergency chemistry within minutes. Without oxygen, mitochondria cannot sustain oxidative phosphorylation, ATP levels fall, and the cell's energy currency runs thin. Ion gradients decay, membranes fail, and tissues begin to injure themselves through swelling and excitotoxic cascades. In the brain, neurons are especially vulnerable because they spend energy constantly just to maintain readiness. When brain function stops, the integrated signaling that supports awareness cannot be sustained, and the global coordination that binds perception and memory fractures. The body does not instantly become inert, but coordination unravels, and that unraveling is the beginning of a new trajectory. What persists is easier to list than what ends, and the list is almost unsettling in its continuity. The body's mass remains and its atoms remain, and their quantum fields remain because fields do not switch off with a heartbeat. The chemical energy stored in bonds remains until reactions release it as heat, motion, or new molecules. The information in DNA remains as a molecular pattern, a sequence of bases that still spells out a genome. Even after death, enzymes and microbes may read and alter that text, but the text does not vanish at the moment of declaration. What changes is organization, and organization is the whole story of life. Metabolism's not a thing you can hold, but a maintained pattern of flows that must be continuously repaired. Neural signaling is not a substance, but a coordinated choreography of electrical and chemical events across billions of synapses. In life, that choreography is stabilized by feedback, blood flow, and constant energy input. Death is the irreversible loss of that choreography at the scale that matters when repair cannot keep up with decay. The difference is not atoms versus no atoms, but pattern versus no pattern. This is where the question becomes larger than biology, because the brain is not just tissue. A living brain is a dynamic system that stores memories, predicts futures, and generates a self that feels continuous. It compresses a lifetime into networks of synaptic strengths, molecular states, and learned habits of activity. When that system fails, we do not only lose function, we lose a point of view, an interior perspective that cannot be photographed. The hard part is not that atoms remain, but that experience seems to stop, and nothing in the room tells us where it went. Classical intuition says off is off, and much of daily life rewards that certainty. In everyday machines, a broken circuit ends the computation, and no hidden layer continues the program. In classical physics, complete knowledge of the present implies a fixed future, at least in principle, and randomness is just ignorance. If the brain is only classical machinery, then death is simply the end of the process, like a clockwork that can no longer tick. That view is clean, and it is emotionally brutal in its finality. Yet modern physics does not describe reality as a clockwork of definite properties, and that shift has a history. In the early 20th century, experiments on light and atoms forced a new language of probabilities and quantized energy. At the smaller scales, outcomes are probabilistic and possibilities coexist until measurement selects a definite result. Quantum theory does not say anything can happen, but it says certainty is constrained by the structure of the theory. It also says information is physical, tied to real states of matter and fields, and cannot be ignored as mere abstraction. This is the core tension we will carry through the series, and it is not a loophole so much as a demand for precision. The medical baseline says the brain's organized activity ends irreversibly, and the person as a functioning system is gone. The conservation baseline says matter and energy persist and transform, indifferent to whether we call the transformation tragic. Quantum theory adds a third layer, asking what counts as information, how it is recorded, and what it means for a record to be accessible. The question is not whether physics is spiritual, but whether our categories are too small. To approach that layer, we need to name the quantum ideas without turning them into mysticism. Superposition means a system can be described as multiple possibilities at once, not because it is confused, but because the mathematics encodes real interference effects. Entanglement means separated systems can share a single joint description, so that their properties are correlated beyond any classical bookkeeping. Measurement links a quantum description to a definite outcome in our experience. and it raises the uncomfortable question of what counts as an observer. These are not metaphors, and they do not automatically scale up to human stories. Then there is decoherence, the quiet workhorse that makes the world look classical, even when the underlying rules are quantum. Interaction with the environment spreads quantum correlations into countless degrees of freedom, like ink dispersing through water. The system's delicate phases become effectively inaccessible, and interference disappears from anything we can control or reverse. Decoherence does not destroy possibilities, but it makes them unusable for coordination, prediction, and memory. In plain terms, the world becomes definite because the environment keeps copying and dispersing information. This matters because brains are warm, wet, and noisy, and they constantly interact with their surroundings at every scale. Neurons sit in salty fluid, membranes flicker with thermal motion, and molecules collide billions of times per second. Whatever quantum events occur inside ion channels or synaptic proteins are rapidly entangled with the environment, and their coherence is expected to decay extremely fast. That does not rule out quantum relevance, but it sets a high bar for any proposed mechanism. Any claim about consciousness surviving death must confront decoherence, not wave it away with mystery. We also need to be careful with the word information, because it carries different meanings in different rooms. In physics, information can mean the distinguishable states of a system, or the correlations between systems, and it can be quantified in bits. In thermodynamics, information links to entropy, the measure of how many microstates fit a macrostate, and to the cost of erasing records. In everyday speech, information means meaning, narrative, and memory, which are higher-level constructs. Those layers relate, but they are not identical, and confusing them creates false hope or false despair. When someone dies, many kinds of information remain in the world, and you can almost picture them as faint trails. The arrangement of molecules in the body encodes a history of development and disease, from scar tissue to plaque to the chemistry of stress hormones. The room contains heat patterns, air currents, and chemical traces, including exhaled molecules that still drift and mix. Outside the room, there are photos, messages, and neural imprints in other brains, each a partial model of the person. Even the electromagnetic noise of the hospital, the radio chatter, the monitoring signals, has interacted with the scene in tiny ways. But the information that seems most precious is the integrated pattern that supported subjective experience, the sense of being someone. If consciousness depends on ongoing computation, then ending the computation ends the experience, even if the hardware remains. If consciousness depends on a special kind of quantum coherence, then we must ask how it was protected against heat and noise while alive. Either way, we must specify a mechanism, not a metaphor, and we must ask what physical substrate carries the relevant correlations. Otherwise, we're only renaming ignorance. This is where quantum physics is often misused, and the misuse follows predictable shortcuts. Some stories claim that because quantum outcomes are uncertain, anything we imagine might be true, as if probability were permission. Others claim that because information is conserved, personal identity must persist, as if a conserved ledger implies a conserved self. These leaps confuse mathematical structure with human meaning, and they skip the hard work of mapping one level to another. We will slow down and keep the categories separate, even when the separation feels unsatisfying. Still, quantum theory does force us to rethink what it means for something to be gone, because gone is often a statement about access. In quantum mechanics, a state can be delocalized, and information can be distributed across correlations that no single part contains. In quantum field theory, particles are excitations of fields that fill space, so the boundary between object and environment becomes less absolute. In thermodynamics, irreversibility is often about practical access, not absolute erasure, because microscopic laws can be reversible while macroscopic processes are not. The universe may keep records that no one can read, so the hook is not that physics proves an afterlife, and it is not that equations replace mourning. The hook is that physics keeps accounts in ways our intuition does not, and those accounts can be surprising. Energy is conserved, but it degrades into heat and becomes less useful for doing work, which is why order is hard to maintain. Information may be conserved in principle, yet scrambled beyond recovery, like a book shredded and mixed into a storm. The question becomes which parts of a person are conserved, and in what form, and whether any of those forms could matter to experience. We will also widen the frame beyond the hospital room, because the universe itself is an information processing arena. The cosmos has horizons, black holes, and expanding space that complicate what it means to store a record and keep it accessible. A photon leaving Earth can carry information outward for billions of years, a tiny messenger that may never return. A black hole can hide information behind an event horizon, an apparent one-way boundary, yet quantum theory insists it cannot be destroyed. That insistence is not sentiment, but a demand for consistency in the laws. That brings us to the documentary's arc, which moves from foundations to consequences without skipping steps. First, we build quantum foundations, including superposition, entanglement, and the role of measurement, and we show how these ideas are tested. Then we confront decoherence and the emergence of classical reality from quantum rules, because that bridge is where many popular claims collapse. Only after that do we ask what these ideas could mean for brains and minds, and what they almost certainly do not mean. Along the way, we will keep asking a simple question: what would we have to measure to know? Next, we move into cosmology and the fate of information at the larger scales, where intuition fails in a different way. We examine black holes, Hawking radiation, and the information paradox. A decades-long argument about whether physics can truly erase a record. We ask what the universe can store, what it can erase, and what it can only scramble beyond retrieval. We connect those ideas to the physical traces every life leaves behind, from heat to photons to altered matter. We also ask how long any record can last in an expanding, aging cosmos. Then we return to the mind with neuroscience and computation, because any claim about survival must pass through biology. We ask what consciousness requires in terms of dynamics, integration, and memory, and what kinds of breakdown correspond to the end of experience. We examine whether any plausible quantum effects could matter at neural scales, given temperature, noise, and decoherence times. We separate poetic possibility from physical plausibility, not to dismiss wonder, but to protect it from fraud. If a proposal is extraordinary, it should come with extraordinary detail. Finally, we take stock of what remains after death in the strict physical sense, and we do it without flinching. Matter returns to cycles, energy becomes heat and radiation, and information becomes records in the environment, some crisp and some faint. Some records persist for a while, like inscriptions in bone or data in archives, and others are overwritten quickly by diffusion and decay. Over cosmic time, even durable structures face entropy and expansion, and the universe becomes less hospitable to organized complexity. The question is not whether anything remains, but what kind of remaining is possible. None of this answers the deepest human question by itself, and it should not pretend to. Physics can describe what happens to atoms, fields, and correlations, and it can do so with ruthless consistency. It can constrain what is possible and what is forbidden, and it can expose where our metaphors break. It cannot declare what it feels like to be dead, because feeling is a first-person fact, not a third-person measurement. The gap between those perspectives is part of the unanswerable, but physics can still narrow the space of honest stories, and that narrowing has value. It can tell us what must remain, what cannot remain, and what would require new laws that we have not yet seen. It can show us that death is not a disappearance of substance, but a collapse of organized process, and that collapse has a physical signature. It can force us to ask whether consciousness is a process that ends, or a pattern that might be preserved in some other register, and it can make us notice how much of a life is already distributed across the world. We end where we began, with a line on a screen and a silence in a room. The body is still part of the universe's inventory, and the universe will not forget that it existed, because forgetting is not a simple option in physics. The question is whether the universe remembers it in a way that matters to the one who lived it. Is a scattered record, heat in the air, photons in space, correlations in matter, anything like continued self? To answer that, we have to enter the quantum world where intuition breaks and accounting becomes strange. Chapter 1 ended with a ledger that never stops updating, even when a mind goes dark. Chapter 2 builds the rules of that ledger at the smallest scales, where certainty is not the default. We're going to linger in the grain of reality, where prediction replaces intuition, and where what happened depends on how information is allowed to exist. Quantum mechanics is not a vibe or a metaphor for mystery. It is a mathematical framework that turns physical assumptions into numbers, and those numbers match experiments to astonishing precision. The theory does not merely gesture at uncertainty, it calculates distributions that laboratories can verify to many decimal places. Historically, this framework was not invented to sound strange. It was forced into existence by stubborn anomalies, black body radiation, the photoelectric effect, atomic spectra, that refused to fit classical physics, when Planck, Einstein, Bohr, Heisenberg, and Schrödinger argued over the rules. They were not chasing poetry. They were trying to make matter and light stop contradicting the evidence. The core object is the wave function, usually written as psi. In the formalism, psi is a state vector in a mathematical space, and its job is to generate probabilities for measurement outcomes. It is not a little wave in space that we can photograph, even when diagrams tempt us to imagine ripples. Think of psi as a compact encoding of what the theory lets us predict, given everything that has interacted with the system so far. It carries information about possible outcomes and the relationships among them, including relative phases that have no classical counterpart. Those phases are not decorative. They are the hidden gears that make interference possible. The wave function assigns amplitudes to possible outcomes, and amplitudes are not ordinary probabilities. Probabilities are real numbers between 0 and 1, while amplitudes can be complex numbers with both magnitude and phase. When we calculate a probability, we take the magnitude squared of the total amplitude, and that squaring is where the surprises begin. When amplitudes add, they can reinforce or cancel, and that interference is the signature. Two routes to the same result can cooperate like synchronized waves, or they can negate like equal forces pulling opposite ways. The cancellation is not philosophical. It is a measurable deficit of events where classical reasoning expects a simple sum. Superposition means the wave function can include multiple mutually exclusive possibilities at once. In the math, the state is a linear combination, and linearity is the engine that lets alternatives coexist. The system is not secretly choosing one option in the background, at least not in standard quantum theory. It is important to say what superposition is not. It is not ignorance about a hidden classical state. Like a card face down on a table, it is a structure that can generate interference, and interference is impossible if the system merely has one definite option we do not know. The most famous demonstration is the double-slit experiment. Send particles toward two openings and ask where they land on a screen. The setup looks like a simple geometry problem, yet it becomes a test of what path even means. Visually, the apparatus is almost austere: an emitter, a barrier with two narrow slits, and a pale screen waiting in the dark. The slits are close enough that their diffracted spreads overlap, which is crucial for interference to have room to appear. In the quiet of the lab, the screen becomes a ledger page where each impact is a single ink mark. If you fire a bright beam, you see a striped interference pattern. Bright and dark bands emerge like a barcode, with spacing determined by wavelength, slit separation, and distance to the screen. The pattern is not a blur of indecision. It is a crisp, repeatable structure that can be predicted before the first run. If you fire one particle at a time, the pattern still appears, built dot by dot. Each particle arrives as a localized event, a tiny flash or a microscopic chemical change. Yet the long exposure reveals the same stripes, as if each particle somehow participated in a wave-like rule. Each single hit looks random, and no hit lands as a half dot. Detectors do not register half an electron or a fraction of a photon in these contexts. The granularity is part of the story. Discrete outcomes, continuous-looking patterns. Yet after many trials, the distribution forms a stable pattern that matches interference. The randomness is not lawless. It is constrained by the wave function's amplitude landscape. The stable pattern is the statistical fingerprint of the underlying state. That pattern is not a story we tell after the fact. It is a quantitative prediction from the wave function, confirmed across electrons, atoms, and photons. Experiments have pushed this into regimes that feel almost absurd. Large molecules sent through interferometers, with coherence preserved long enough to show fringes. The lesson is precise and unsettling. Quantum theory predicts individual outcomes only probabilistically, while predicting ensemble patterns with near-perfect reliability. It is as if nature refuses to commit to a single dot in advance, yet commits strongly to the final histogram. A useful analogy is a map of tendencies rather than a list of certainties. The wave function is a rule for how to compute the odds of different results, given an experimental context. It does not tell you which dot will appear, but it tells you where dots will cluster over time. But the analogy breaks if we forget interference. Classical probabilities never cancel each other, while quantum amplitudes can, which is why the stripes exist. In classical thinking, two possible routes simply add their chances and nothing ever subtracts. So what changes when we measure which slit the particle used? The interference disappears, and the pattern becomes two broad humps. The screen stops showing alternating bright and dark bands, and it starts looking like a mundane sum of two single slit spreads. Popular accounts often say the particle knows it is being watched. That language is intuitive, but it smuggles in a human observer as if required. It also suggests psychology, where the real mechanism is physics: correlation, entanglement, and information flow. In physics, measurement is not a glance. Measurement is an interaction that correlates the system with something else, leaving a record in matter. The record can be as small as a scattered photon's change direction, or as large as a macroscopic detector click. A detector near a slit couples to the particle's path degree of freedom. That coupling entangles the particle with the detector, and the joint state changes. The detector does not need to be intelligent, it only needs to have states that differ depending on the path. Entanglement means the wave function now describes the particle and detector together. The particle's path is no longer an isolated variable with its own pure state. Instead, the path becomes correlated with detector states, and those correlations are what matter. Once the detector carries path information, even in principle, the phases that produced interference become inaccessible. The stripes vanish because coherence is lost. More precisely, the off-diagonal terms of the system's reduced density matrix are suppressed when we ignore the detector's degrees of freedom. This is the first bridge to the macroscopic world. The quantum system does not need a mind to collapse. It needs an environment that can store distinguishing information, because distinguishability is what kills interference. To see why, imagine the detector is automated and sealed. The device records which slit, and no human checks it until tomorrow. The lab can be empty, the lights off, and the data locked away. The interference is still gone today. The pattern does not wait for a person to open a box, because the physical correlation already exists. The world has already paid the price of information, coherence traded for record. This point is not philosophical. It is tested in many forms, including delayed choice experiments and quantum eraser setups that manipulate available information. These experiments are designed to stress our storytelling instincts, while leaving the mathematics untouched. Delayed choice experiments show that changing what is measured changes which pattern appears, even when the choice is made after the particle enters. The timing feels like a trap for common sense, because the apparatus seems to decide the past, yet the results still follow quantum predictions without invoking awareness. In practice, the delayed choice is implemented with fast switches, beam splitters, and detectors whose settings are changed while the photon is already in flight. The crucial point is that quantum theory assigns probabilities to entire experimental arrangements, not to imagined classical trajectories. The data align with that rule, even when our narrative wants a simpler timeline. Quantum eraser experiments show that if path information is erased in a specific way, interference can be recovered in correlated subsets. The key variable is information in physical degrees of freedom. When which path markers are made indistinguishable again, the phase relationships can reassert themselves, though typically only when you sort the data by the appropriate partner outcomes. This sorting matters, and it is often misunderstood. The recovered interference does not usually reappear in the raw, unsorted screen pattern, because the witch path record still exists somewhere in the joint system. What changes is that, within a selected subset where the record is effectively erased, the correlations reveal fringes that were hidden in the aggregate. So what is collapse in the formalism? In textbook quantum mechanics, collapse is a rule that updates the wave function after a measurement outcome. Before measurement, we evolve the state smoothly with Schrödinger's equation, and after measurement, we replace the state with one compatible with the observed result. That rule works, but it raises a question that has haunted physics for a century. When exactly does the smooth evolution stop, and when exactly does the discontinuous update occur? The formalism seems to contain two kinds of time evolution, and the boundary between them is not written into the equations. In one family of interpretations, collapse is not a physical event in space. It is an update of our description when we learn which outcome occurred. This view treats the wave function as a tool for encoding knowledge, and collapse as Bayesian-like conditioning, though the details are distinct. In another family, collapse is real and dynamical, like an added physical process. Objective collapse models propose tiny random collapses that grow with system size. They are motivated by the desire to make measurement a physical phenomenon, not a rule about observers. Both approaches agree on the same lab predictions in ordinary regimes. The difference is what they claim about reality between measurements. In other words, the dispute is not about the stripes on the screen, but about what we're allowed to say when no record exists. There is also the many worlds approach, where the wave function never collapses. Measurement creates branches where different outcomes are recorded in different correlated histories. The branching is not a special act. It is the natural consequence of unitary evolution applied to large entangled systems. Many worlds sounds extravagant, but it keeps the equation simple. It treats the appearance of a single outcome as a consequence of entanglement and decoherence. The price is conceptual, accepting that the universal wave function contains mutually inaccessible records. The documentary does not need to pick a favourite interpretation here. We need the shared operational core that all working physicists use to build devices. This is the part that survives regardless of metaphysical preference. That core says, measurement is physical interaction plus record formation. The record can be a detector click, a chemical change, a scattered photon, or a shifted current. What matters is that the record is stable enough to be consulted later, even if later is a microsecond. Now we introduce decoherence, because it explains why macroscopic objects do not show obvious superpositions. Decoherence is not a mystical collapse. It is entanglement with the environment, followed by our practical inability to track the environment's enormous number of degrees of freedom. Every system is surrounded by air molecules, photons, vibrations, and internal degrees of freedom. These interactions constantly copy information about the system into the environment. Even in a vacuum chamber, blackbody radiation and stray fields can carry away clues. When the environment carries away phase information, the system's interference terms become effectively unobservable. The system behaves as if it were in a classical mixture. The underlying global state may remain pure, but the local description becomes mixed when we trace out what we cannot access. Decoherence is fast for large, warm, complex objects. It can be unimaginably fast for everyday items, because there are so many ways to leak information. A dust grain in sunlight is bombarded by photons that scatter and encode its position almost instantly. This is why we do not see tables in two places at once. It is not that quantum rules stop applying, it is that coherence becomes practically impossible to maintain, because the environment is continuously monitoring certain variables. The key word is practically, because the underlying evolution can still be unitary in many models. The information is not destroyed, it is dispersed into correlations we cannot track, like a message shredded and blown into a storm. In the ledger metaphor, decoherence is like shredding a clean record into countless microscopic fragments. The account still exists in principle, but it is no longer readable as one page. To reconstruct it, you would need to gather and phase align an astronomical number of environmental degrees of freedom. This matters for claims about brains and consciousness. Brains are warm, wet, and chemically active, and they are coupled to the environment at every moment. They are also internally noisy, with constant molecular motion that acts like an environment within the skull. Neural signaling depends on ions, membranes, neurotransmitters, and electrical fields in salty water. Those ingredients are constantly jostled by thermal noise and collisions. At body temperature, the typical thermal energy is enough to scramble delicate phase relationships quickly, unless a system is specially protected. If a delicate quantum superposition were essential to thought, it would need protection from decoherence. It would need error correction, isolation, or some robust mechanism we can specify. Without such a mechanism, coherence would fade before it could influence large-scale neural dynamics. Some researchers explore quantum effects in biology, including photosynthesis efficiency and avian magnetoreception. These cases involve specific molecules and timescales, not vague consciousness claims. The interest is legitimate because biology can exploit quantum chemistry, especially when structures constrain motion and reduce certain noise channels. Even if quantum events matter in some biological processes, that does not imply the brain sustains large-scale coherent superpositions. The burden is to show a pathway from microcoherence to cognition. That pathway would need to identify where coherence lives, how long it lasts, and how it couples to neural computation. So we confront the popular claim directly. Does consciousness cause collapse, making the mind a special ingredient in physics? The claim persists because it feels like it honors experience, and because quantum measurement sounds like it needs an experiencer. Historically, the idea has roots in early debates about measurement. Von Neumann formalized a chain from system to apparatus to observer and asked where to place the cut. His analysis sharpened the problem. If everything is quantum, then the apparatus should also be described by a wave function. Wigner later speculated that consciousness might complete the measurement, partly to avoid an infinite chain of quantum descriptions. These were philosophical moves, not experimental necessities. They were attempts to make sense of a formalism that seemed to require a classical domain, even while claiming universality. Modern physics does not require that move. Decoherence and quantum information theory explain why definite outcomes appear without invoking a conscious witness. The appearance of classicality can be derived as an emergent stable regime produced by environmental entanglement. Experiments routinely perform measurements with no human present at the moment of interaction. Automated detectors run overnight, satellites record photons in space, and data is analysed long after. The world does not pause until a graduate student opens a file. In particle physics, detectors at colliders register events that no one experiences directly. The observer is silicon, gas, scintillator, and electronics, all obeying quantum and classical laws. A particle track is a chain of ionizations, and each ionization is a microscopic record that amplifies into a macroscopic signal. In astronomy, a photon can be absorbed by dust in interstellar space. That absorption is a measurement in the physical sense, because it leaves a record in the dust state. The dust grain's vibrational modes change, its temperature shifts slightly, and the surrounding radiation field carries away the difference. If consciousness were required, the universe before life would be a paradox. Stars formed, nuclei decayed, and cosmic background photons scattered long before any brains existed. The early universe was a furnace of interactions, and interactions are what measurement reduces to. Quantum theory still describes those processes, and the universe did not wait for observers to become real. The myth of the magical observer confuses knowledge with interaction. Knowledge is what a mind has, while interaction is what matter does. This does not demote consciousness to nothing. It places consciousness where science can handle it, as a physical process implemented by matter and energy in specific arrangements. The mystery remains profound, but it is not a loophole in the measurement postulate. So what is the correct role of an observer in quantum mechanics? An observer is any system that becomes correlated with another system in a way that can store a stable record. The observer does not have to be alive, and it does not have to understand what it records. A human observer is a special case because humans interpret records and assign meaning. Meaning is real in experience, but it is not a required term in the measurement postulate. Physics can describe the ink on the page without describing the story it tells. Now, we return to superposition with one more concrete anchor. Consider a single photon entering a beam splitter, with two possible paths to two detectors. The beam splitter is a simple optical element, yet it acts like a fork in the wave function's road. Quantum theory assigns an amplitude to each path, and the photon can be in a superposition of both. If the paths recombine, interference determines which detector clicks. With the right phase settings, one output can become bright and the other dark, as if the photon chooses by interference rather than by route. If we place a device that marks the path, interference disappears. The click statistics change, not because of attention, but because the physical correlations changed. The marker can be as subtle as a polarization tag, and even that can be enough to make the alternatives distinguishable. This is the same logic as the double slit, expressed in a cleaner optical circuit. It is also the logic behind quantum computing, where coherence is a resource. A quantum algorithm is essentially a carefully choreographed interference pattern in an abstract space of possibilities. Quantum computers work only if superpositions and entanglement are protected from decoherence long enough to compute. The engineering challenge is precisely to prevent uncontrolled measurement by the environment. That is why devices are cooled, shielded, isolated, and corrected, because the environment is always trying to learn what the qubits are doing. That engineering challenge is a clue about brains. If coherence were central to consciousness, evolution would need to solve a problem that engineers struggle with in cryogenic labs. It would need a biological method for isolating, stabilizing, and error-correcting fragile quantum states amid heat and chemical chaos. That does not make it impossible. It makes it a claim that must be supported by specific structures, timescales, and measurable signatures. The question becomes concrete. Where is the coherence? How is it protected? And what experiment could falsify the proposal? So far, the mainstream view is conservative. The brain's relevant dynamics appear well described by classical electrophysiology and chemistry, with quantum mechanics underlying the components, but not producing macroscopic coherence. Neurons behave like noisy, non-linear electrical devices, and their collective behavior can be modeled without invoking long-lived entanglement. Still, quantum physics matters to the brain in a quieter way. Chemistry is quantum, bonding is quantum, and the stability of molecules depends on quantum rules. The very existence of stable atoms, selective ion channels, and reliable neurotransmitter binding is grounded in quantum structure. The brain is classical in behavior because decoherence selects stable pointer states. Those states are the ones that survive environmental monitoring and can support reliable memory and control. In plain terms, the world keeps checking certain properties so often that they become the only ones that persist. This is the emergent story. The microscopic world is quantum, but the macroscopic world is a special regime where quantum information is constantly leaked and redundantly recorded. Classical reality is not a separate substance, but a stable pattern produced by relentless copying into the environment. That redundancy is why reality feels shared. Many parts of the environment carry consistent information about the same macroscopic facts, like the position of a chair. Light reflects off the chair into countless eyes and cameras, and air molecules bounce off it into countless other records. In quantum information terms, the environment acts like a communication channel that broadcasts certain variables. The broadcast makes those variables objective for many observers. Objectivity, in this sense, is not metaphysical certainty. It is agreement enforced by redundant physical records. This is sometimes called quantum Darwinism, because stable states proliferate through copying. Again, no consciousness is needed, only interaction and redundancy. The winners are the states that can survive being monitored, because they imprint themselves without being destroyed. Now we connect this foundation back to the documentary's central question. When a person dies, what changes in the universe's record of energy and information? If the ledger never stops updating, then death is not an erasure of physics, but a reorganization of what can be maintained. If consciousness is not a special trigger for collapse, then death is not a quantum switch that releases a soul from measurement. It is the end of a biological process that maintains certain patterns. The patterns are not mystical. They are physical arrangements that required constant work. The brain in life is a system that constantly measures itself and its world. Neurons integrate signals, update synapses, and create durable records in molecular and network states. At every moment, the brain is both processing information and being processed by its environment. Those records are physical, and they are maintained against noise by metabolism. The living brain spends energy to keep its informational structures within functional bounds. It repairs membranes, pumps ions, clears waste, and stabilizes chemical gradients that would otherwise dissolve. Death removes that maintenance. Oxygen stops, ATP falls, ion gradients decay, and organized electrical activity fragments then fails. The familiar rhythms, coordinated firing, synchronized oscillations, stable connectivity, lose the energetic support that keeps them coherent in the classical sense. From a quantum perspective, nothing magical happens at the moment of death. The atoms still obey quantum laws, and the environment still entangles with them relentlessly. Photons still scatter, molecules still collide, and thermal motion still explores possible configurations. What changes is the kind of information the system can preserve. A living brain can store and refresh patterns that support memory and self-model. A dying brain cannot, because the mechanisms that correct drift and noise are no longer powered. The ledger still updates, but the entries shift from controlled computation to uncontrolled relaxation. Correlations that once supported experience disperse into heat, chemical diffusion, and microscopic entanglement. The physical record becomes more like a spreading stain than a maintained inscription. This is a hard boundary to state cleanly. Physics can track energy flows and molecular changes, but it cannot directly read subjective experience from the outside. We can correlate reports with brain activity, yet the first-person point of view remains private in a way instruments cannot directly capture. So we keep the question narrow and testable. Could any quantum coherent process plausibly contribute to consciousness? And if so, what happens when the system stops? The answer must be built from mechanisms, not from the romance of uncertainty. If coherence is irrelevant, then death ends consciousness because the classical computation ends. The remaining information is scattered in the environment, not organized as a point of view. The body becomes a system moving toward equilibrium, and equilibrium is the enemy of structured memory. If coherence is relevant in some limited way, then death still likely destroys it quickly, because decoherence accelerates when regulation fails and temperature gradients change. As membranes break down and chemical conditions shift, the environment gains even more channels to record distinctions, and coherence becomes even harder to protect. Either way, the idea that a mind collapses reality is not supported by modern measurement theory. The mind is part of reality's physical chain, not its external trigger. Consciousness may be extraordinary, but it is not a special exemption from interaction. This chapter's foundation is meant to remove a common loophole. Quantum mechanics is strange, but it is not a blank check for survival claims. The strangeness is disciplined by equations, and those equations are disciplined by experiments. Yet the strangeness still matters, because it reframes what it means to lose information. The universe may keep correlations even when they are inaccessible, and that complicates simple narratives of vanishing. When coherence disperses, it does not necessarily disappear. It becomes encoded in relationships too fine-grained to retrieve. We end with a transition from rules to consequences. If measurement is interaction and decoherence is ubiquitous, then the brain's quantum story is mostly about how classical stability emerges. The ledger is still being written, but it is written in the language of correlations rather than the language of souls. Next, we ask what the universe does with information at larger scales, where horizons and gravity enter. The ledger is still balanced, but the bookkeeping becomes cosmic. Chapter 1 left us with a universe that never stops keeping accounts of energy and information, a ledger written into every interaction. Chapter 2 showed how quantum rules become classical facts through measurement and decoherence, how possibilities narrow into outcomes once the world records them. Now we bring that ledger into the skull, where wonder meets biology and hard constraints. We move from clean equations to living tissue, where heat, water, and salt never stop jostling the parts. The question is not whether quantum mechanics exists in the brain, because it must. The question is whether it matters for consciousness in a direct organizing way, whether it shapes the story, not just the ink. Start with what is real and measurable in living systems, because biology is not exempt from physics. Quantum mechanics is not optional in biology, because chemistry is quantum, and chemistry is the engine of life. Bonds form because electron wave functions overlap in specific geometries, and those geometries are quantized. Electron orbitals are not tiny planets, but standing wave patterns, probability clouds with discrete energies. Reaction rates depend on energy gaps, barrier heights, and the distribution of molecular vibrations, all of which are quantum in origin. In a visual sense, imagine a cell as a crowded night market lit by thermal motion. Molecules collide, twist, and reorient, while enzymes stand like scaffolds that guide traffic. Even in that crowd, quantum rules quietly decide which pathways are allowed and which are forbidden. The cell does not use quantum as a slogan, it simply cannot avoid it. One of the clearest testable places where quantum affects matter is enzymatic catalysis. Enzymes speed reactions by factors of millions or more, and they do it by shaping an energy landscape. Classical chemistry describes barriers that reactants must climb over, like hills between valleys. Quantum mechanics adds another option. Particles can sometimes tunnel through barriers rather than surmount them. In enzymes, electron tunneling can speed reactions that classical barriers would slow, especially when donor and acceptor sites are positioned with nanometer precision. In some cases, protons also tunnel across energy barriers during catalysis, and that matters because protons are light. A proton is nearly 2,000 times lighter than a carbon atom, so its quantum wavelength is comparatively large at biological scales. That makes tunneling more plausible, particularly when hydrogen bonds create narrow barriers. These effects are measurable and modelled with quantum chemistry, not metaphors, using isotope substitution and temperature dependence to test tunneling signatures. Proton transfer is central in many biochemical steps, including hydrogen bonding networks that stabilize proteins and guide reactions. A hydrogen bond is not just a static stick between atoms, but a dynamic relationship shaped by vibrations and electronic polarization. Quantum effects can change reaction pathways, alter kinetic isotope effects, and shift temperature dependence in ways classical models struggle to match. The key point is scale and context, not cosmic significance. These are local quantum advantages, not global quantum minds. Historically, this is part of a longer story about how quantum theory entered biology. Early 20th century physicists debated whether life required new laws, and some imagined a special vital force. As molecular biology matured, the opposite happened. Life became a showcase for ordinary physics applied to extraordinary complexity. Schrödinger's famous question, "What is life?" helped frame heredity as an information problem, but the chemistry of that information still follows quantum rules. The modern view is less romantic and more powerful. Life is not outside physics, it is physics organized. Photosynthesis offers another confirmed case where quantum language is useful, and it comes with striking visuals. Picture sunlight arriving as a stream of photons, each one a packet of energy. When a photon is absorbed by a pigment molecule, it excites an electron into a higher energy state. That excitation often behaves like an exciton, an energy packet shared across molecules rather than pinned to one site. The exciton moves through pigment-protein complexes toward a reaction center, where chemical energy is stored. Experiments have shown signatures consistent with short-lived coherence aiding efficient energy transport, at least in some systems under some conditions. Coherence here means that multiple pathways can interfere, like ripples overlapping on a pond. The protein environment can, paradoxically, help by guiding the excitation through a structured landscape. Yet the coherence is not a mind-like superposition, and it is not a long-lived quantum memory. It is a transient wave-like behavior in a molecular network shaped by structure and environment. That coherence lasts long enough to influence yield, then it decoheres into heat and chemistry. The visual is a brief shimmer, an organized phase relationship, followed by the ordinary bustle of thermal motion. In the ledger metaphor, coherence is a delicate kind of bookkeeping that the environment can erase by learning which path information. Once that information leaks into vibrations, solvent motions, or surrounding proteins, the interference fades. What remains is classical chemistry continuing its work. Avian magnetoreception is another frontier where quantum mechanisms are plausible, and it shows how narrow these claims can be. Some birds navigate using Earth's magnetic field with sensitivity that is hard to explain classically. The field is weak, far weaker than a refrigerator magnet, yet it appears to influence behavior reliably. A leading model uses radical pair chemistry, where two electrons are created in a correlated spin state. Their spin configuration can affect which chemical products form, and those products can become signals. Again, the claim is narrow and testable, and that is what makes it scientifically interesting. Specific molecules in the retina could maintain correlated spin states briefly, long enough for a reaction to choose a pathway. Magnetic fields shift those correlations and bias chemical signals that the nervous system can read. The key word is briefly. Microseconds can be meaningful in chemistry, even if they are short by cognitive standards. So quantum biology is real, but it is not a blank check. It appears in specialized molecular settings where evolution can exploit quantum chemistry, often by shaping geometry and controlling noise. It does not automatically imply long-lived coherence across neurons or across whole brain networks. The distance between a tunneling proton and a conscious thought is not just a gap of scale, but a gap of mechanism. This distinction matters because popular stories often skip the middle steps, and the middle steps are where the difficulty lives. They jump from quantum effects in molecules to quantum consciousness in the self, as if one implies the other. The bridge requires mechanisms that survive heat, noise, and constant interaction, and it must specify how microscopic quantum states become macroscopic cognitive differences. Without that bridge, quantum becomes a mood rather than an explanation. Now we describe the brain's operating conditions with no romance added, because conditions set the limits. The brain is warm, wet, and electrically active in salty water, and every one of those adjectives matters. Warm means thermal agitation is strong, constantly randomizing phases and jostling structures. Wet means water molecules form a restless bath of dipoles that couple to charges and fields. Salty means ions screen electric fields and collide with proteins, creating fluctuations that carry away information. Visually, a neuron is not a quiet wire, but a living coastline. Membranes ripple, proteins open and close, and ions surge like tides through channels. The extracellular space is narrow, packed with glial processes and connective tissue, and the intracellular space is crowded with cytoskeletal filaments and organelles. In that crowd, isolation is hard to come by, and isolation is what coherence usually needs. At body temperature, decoherence is typically fast for large, complex degrees of freedom. Coherence is fragile when many environmental channels can record distinguishing information, because each channel becomes a witness to the system's state. The brain is an environment rich in such channels, even inside itself, with photons, phonons, molecular vibrations, and electromagnetic noise all acting as record keepers. Decoherence is not a mysterious force, but the ordinary spread of information into many degrees of freedom. Neural computation depends on ion gradients across membranes, maintained by molecular pumps that spend ATP. Action potentials are collective electrical events involving many ions and many water molecules, not single electrons traveling like bullets. Sodium and potassium ions move through channels in coordinated waves, and the membrane voltage changes by tens of millivolts across micrometer distances. Those ions and molecules constantly interact with their surroundings and rapidly entangle with them, which makes stable phase relationships difficult to preserve. If a quantum superposition were to influence cognition, it would need a protected substrate, something that can keep quantum phases aligned long enough to matter. It would need coherence times long enough to affect neural decision points, which often unfold over milliseconds and longer. It would also need a coupling pathway that changes firing, plasticity, or network dynamics, because consciousness is not a private event inside a molecule. The quantum state would have to reach the level where neurons and circuits behave differently. In engineered quantum devices, coherence is protected by isolation, cooling, and error correction, all of which are expensive. Superconducting qubits sit near absolute zero, shielded from stray fields and vibrations. Trapped ions float in vacuum under carefully tuned lasers, and even then their coherence is fragile. The brain does not look like a cryogenic lab, and it does not have obvious error-correcting codes designed for qubits. Any claim that it performs quantum computation must specify how biology solves comparable control problems. This is where speculation begins, and we name it clearly rather than dismissing it. Quantum mind theories propose that consciousness depends on quantum coherence, entanglement, or collapse-like events, not merely on quantum chemistry. The most famous is OR, associated with Roger Penrose and Stuart Hameroff, which sits at the boundary between physics, neuroscience, and philosophy. It is ambitious, and ambition is not a flaw, but ambition raises the evidential bar. OR argues that microtubules inside neurons support coherent quantum states, and that these states undergo an objective reduction. The proposal links that reduction to gravity or space-time structure, suggesting that collapse is not only about measurement, but about fundamental thresholds. The theory aims to connect subjective experience to a basic physical process, as if consciousness is tied to how reality chooses outcomes. It is a bold attempt to make the hard problem a physics problem. Microtubules are real and essential for cell structure and transport, and that is worth lingering on. They are hollow cylinders built from tubulin proteins, forming part of the cytoskeleton. In neurons, they help maintain axonal structure, guide growth, and serve as tracks for molecular motors that carry cargo. Under a microscope, they appear as orderly filaments running through the cell, a kind of internal architecture. The speculative step is that they also function as long-lived quantum information processors. Proponents point to ordered geometry, hydrophobic pockets, and possible shielding within microtubule lattices. They argue that certain regions could reduce decoherence by limiting interactions with water and ions. They also suggest that coherent excitations, perhaps involving dipole oscillations or electron distributions, could persist longer than naive estimates. In their picture, many microtubules could become orchestrated, coordinating collapses into discrete moments of conscious experience. The word orchestrated is doing heavy work, and it demands a mechanism. Critics focus on decoherence, and on missing evidence of relevant quantum states in vivo. Warm, wet cytoplasm is expected to destroy delicate phase relationships quickly, especially for large assemblies. Even if microtubules host quantum effects, the question is whether they causally shape neural computation, rather than merely existing as background physics. A second question follows closely. How would microtubule quantum states influence synapses and spikes, the currency of neural signaling? Without a clear coupling path, the theory risks becoming disconnected from measurable neuroscience. Another criticism is explanatory redundancy, which is not an insult but a methodological filter. Many features of cognition and perception are modeled using classical neural dynamics, including attractor networks, oscillations, and synaptic plasticity. A quantum layer must add predictive power, not only philosophical appeal, and it must do so in a way experiments can target. Otherwise, quantum language becomes a decorative overlay on classical mechanisms that already work. There are also broader quantum coherence proposals that avoid microtubules, and they vary in specificity. Some suggest coherence in ion channels, where selectivity filters and narrow pores might support quantum effects in conduction. Others look at synaptic proteins, receptor conformations, or neurotransmitter release, where molecular events can be probabilistic and sensitive to small changes. Some propose that quantum randomness influences neural noise and thus decision-making. These ideas are not all equivalent, and many are deliberately modest. Quantum randomness does exist at microscopic scales, including in molecular events like ion channel gating and vesicle fusion. Yet randomness alone is not a mechanism for consciousness, because noise is easy to get and hard to organize. The question is whether quantum correlations, not just quantum uncertainty, are organized and functionally used. Correlation is the key, because correlation can carry structure across parts of a system. Without correlation, quantum effects may simply average out into classical variability. So what would count as evidence, in a way that could change minds rather than harden camps? First, measurable coherence in specific brain structures, with timescales relevant to neural processing, not merely femtosecond chemistry. Second, a demonstrated causal influence on neural computation, not a correlation that could be classical. The causal link must show that disrupting the quantum feature changes cognition in a specific, predicted way. Third, reproducible experiments that distinguish quantum models from classical biochemical ones. That could include interference signatures, entanglement witnesses, or controlled perturbations that only quantum coherence would explain. It could also include clear scaling predictions where changing temperature, isotopic composition, or magnetic fields shifts outcomes in ways classical models cannot match. The bar is high because the claims are strong, and strong claims should sharpen experiments. We also need to avoid a category error that keeps returning, because it confuses levels of description. Quantum mechanics underlies all matter, including neurons, but that does not mean the brain is a quantum computer. Classical behavior is what quantum systems look like after decoherence selects stable states and suppresses interference. In everyday conditions, the world is quantum underneath, and classical on top, like a deep ocean with a calm surface. In that sense, the brain is already quantum in the same way a rock is quantum, and that is not a punchline. The interesting question is whether it retains non-classical resources long enough to compute differently. Without that, quantum talk adds mystique but not explanation, and mystique is not a mechanism. The ledger metaphor helps here, because it reminds us that information is always being written somewhere. Now we shift to neuroscience's current working picture of consciousness, because it is where measurement has accumulated. It is not a final theory, but it is grounded in decades of electrophysiology, imaging, lesion studies, and computational modeling. Consciousness appears tied to large-scale neural dynamics, integration, and recurrent processing, rather than to a single microscopic site. The brain's activity is not a static map, but a moving pattern that changes with attention, arousal, and context. The brain is not a single processor, but a network of networks, layered and interconnected. Information flows through thalamocortical loops that regulate sensory gating and wakefulness. It flows through cortical hierarchies that transform raw input into abstract representations. It flows through distributed assemblies that bind features into coherent scenes and decisions. Conscious experience seems to require coordinated activity across many regions, not isolated local events. Theories differ in emphasis but converge on certain motifs, and those motifs are testable. Global workspace models emphasize broadcasting and access across systems, as if consciousness is what becomes globally available. Integrated information approaches emphasize irreducible causal integration within a network, asking how much the whole constrains itself beyond its parts. Recurrent processing theories emphasize feedback loops rather than one-way feed-forward sweeps, because feedback can stabilize and refine perception. Predictive processing emphasizes the brain as a model builder that minimizes error, constantly comparing expectation to input. These frameworks are debated, but they share a commitment to dynamics and connectivity, and that matters for our ledger theme. They treat consciousness as something maintained through ongoing interaction, not stored like a file. They also imply vulnerability, because maintenance requires energy and coordination. A moment of experience is not just a snapshot, but a stabilized trajectory through neural state space. In this view, consciousness is emergent from organized activity at scale, and emergence has a precise meaning. Emergent does not mean mystical or outside physics, and it does not mean anything goes. It means the relevant description is at the level of patterns, interactions, and collective behavior, where new regularities appear. A hurricane is made of air molecules, but you do not predict its path by tracking each molecule. Likewise, a conscious episode may depend on neurons without being usefully described at the molecular level. Emergence also does not mean solved, and the mystery remains in a disciplined form. We still do not have a complete account of why certain dynamics feel like something from the inside, yet we can map conditions that correlate with awareness, like wakefulness, anesthesia, seizures, and coma, and those correlations constrain theory. We can ask what changes when experience fades, and what returns when it reappears. We can also measure signatures of integration and complexity, using perturbations and responses. Under deep anesthesia, long-range connectivity and responsiveness often decrease, and the brain's reactions become more local. In disorders of consciousness, certain network dynamics degrade in characteristic ways, and some pathways fail to sustain recurrent loops. These observations do not answer every philosophical question, but they describe the machinery that must be running for a point of view to exist. This matters for our central question because it anchors what death does to the brain, without metaphors that drift. If consciousness depends on sustained, integrated processing, then it requires energy, circulation, and stable cellular function. It is a maintained process, not a static object, and maintained processes can fail abruptly. The ledger keeps counting, but the pattern that counts as you may not. Now we bridge from life to the moment the ledger changes entries, and we do it step by step. When oxygen delivery stops, neurons begin to fail within minutes because their energy budget is tight. The brain stores little fuel, and it depends on continuous blood flow for oxygen and glucose. ATP drops, ion pumps slow, and membrane potentials drift toward collapse. The gradients that once separated inside from outside begin to flatten. As gradients decay, neurons depolarize and release neurotransmitters uncontrollably, because the usual gating breaks down. Excitotoxic cascades can follow, damaging cells through calcium influx and metabolic stress. Calcium is a powerful signal when controlled, but a destructive one when uncontrolled, activating enzymes that degrade membranes and proteins. Synapses fail, and coordinated signaling fragments into disorganized activity. Electrical rhythms that once carried information lose their structure, and the change can be visualized. On an EEG, organized oscillations can give way to slowing, then to silence, depending on conditions. Local circuits may fire briefly in abnormal patterns, then fall silent as energy reserves vanish. The organized, recurrent loops that support integration cannot be sustained without energy and homeostasis. The system can no longer keep its own state within narrow bounds. From the outside, this looks like a shutdown of computation, and the metaphor is not far off. From the inside, if experience depends on those computations, the point of view ends when the dynamics can no longer cohere. The ledger keeps updating, but the self as a process stops being maintained. Matter remains, but the organized flow that made it a mind breaks apart. This is where the question changes shape, and we say it plainly to avoid confusion. Instead of asking where consciousness goes, we ask what happens to the information pattern that was a person. We ask what parts of that pattern persist as physical traces, and what parts dissipate irreversibly. The shift is subtle but decisive, because it turns a destination question into a dynamics question. Some information remains in stable forms like DNA sequence and tissue structure, at least for a time. Some remains in other brains as memories and learned behaviours, which are themselves physical patterns in synapses and networks. Some remains as records in devices, writing and images, which are physical states in matter, magnetic domains, charges in flash cells, ink on paper. These are durable ledgers, though none of them are the original process. But the integrated, real-time pattern that constituted a living mind is different, and it is more fragile than we like to admit. It is a dynamic arrangement of synaptic strengths, firing patterns, neuromodulators, and ongoing feedback. It includes the timing relationships that bind perception, the background tone of arousal, and the constant updating of internal models. When metabolism stops, that arrangement stops being updated and protected, and drift becomes decay. From a quantum perspective, death does not release a coherent soul from the brain, because coherence is not something that waits politely. Decoherence does not pause, and the environment continues to entangle with everything, including the molecules that once supported neural function. If anything, the loss of regulation increases uncontrolled interactions and speeds the scrambling of fine-grained correlations. The ledger becomes noisier, not clearer, as constraints loosen. If quantum coherence played a role in cognition, it would likely be even more fragile during dying, not more liberated. Temperature gradients shift, membranes break down, and chemical noise increases as compartments fail. pH changes, ions leak, and proteins begin to unfold, exposing surfaces that interact strongly with water. Whatever coherence existed would be harder to sustain, not easier, because the environment becomes more invasive. The conditions become the opposite of protection. So we keep the mystery, but we tighten the logic, and tightening is a form of respect. Quantum physics does not confirm an afterlife, and it does not forbid all unknowns, because science rarely forbids what it cannot define. It tells us what would be required for quantum states to matter at brain scale, and it demands measurable signatures. It also reminds us that information is physical, and physical information is always embedded in interactions. The honest stance is a boundary line, not a final verdict carved in stone. Quantum biology is real in specific molecular processes, where coherence or tunneling can be demonstrated and modelled. Quantum mind theories remain speculative until they show durable coherence and causal impact on neural computation. The boundary is not a wall against wonder, but a filter that keeps wonder connected to evidence. This chapter is not a debunking of wonder, and it is not a demand that mysteries be small. It is a sorting of claims into what is measured, what is plausible, and what is currently unsupported. That sorting protects the central question from becoming a story that cannot be tested. It also clarifies where new experiments could actually bite, where the ledger could, in principle, show a new kind of entry. Now we turn the ledger outward again. If the brain's self is a maintained pattern, then death is the collapse of that pattern, not the disappearance of matter. The next question is what the universe does with patterns and records at the larger scales. Next, we follow information beyond the body into horizons, gravity, and cosmic bookkeeping. The ledger still balances, but the meaning of preservation becomes stranger when the universe itself is the archive. Chapter 3 kept us inside the skull, where biology constrains every quantum daydream and forces every thought to ride on chemistry. Now we pivot from consciousness to information, because physics can define information precisely. The shift matters, because information has units, limits, and costs that do not care about our metaphors. The opening hook still stands, and it becomes sharper the closer we look. The universe keeps perfect accounts of energy and information, even when the accounting is hidden in correlations. When a mind goes dark, we ask what changes in the ledger of reality, and whether anything like a person can remain in the fine print. In physics, information is not meaning, intention, or narrative, even though those are what we care about. Information is the specification of a physical state among alternatives, a way of saying which possibility is real. It is the difference between many possible microconfigurations and the one that is actually realized. Start with a simple distinction, because it is the spine of the chapter. A macro state is what you can describe with a few bulk variables, like temperature, pressure, or density. A microstate is the exact arrangement of all particles and fields consistent with that bulk description, down to positions, momenta, and internal quantum states. Visually, imagine a box of gas rendered as a swarm of points, each point a molecule tracing a jittering path. From far away, the gas looks calm, and a few numbers seem to say it all. Up close, the scene is restless. Collisions, ricochets, and ceaseless rearrangement that never repeats exactly. A glass of water has a temperature and pressure that feel complete, as if the description closes the case, yet the molecules can be arranged in astronomically many ways while keeping those same macroscopic numbers. The macrostate hides detail, and that hidden detail is physical information. This is not a philosophical trick, and it is not just a limitation of human language. The hidden detail corresponds to real degrees of freedom that can, in principle, affect the future. If you knew the exact microstate, you could predict the next instant more precisely, because the equations would have more to work with. Entropy is the bookkeeping term for that hidden detail, and it arrived with a long history of confusion. In Boltzmann's form, entropy measures how many microstates correspond to the same macrostate. More microstates means higher entropy, which also means more missing information about the exact configuration. Boltzmann wrote the idea in a single line, S equals K times the log of W, and then carved it into his tombstone. That line is a bridge between counting and thermodynamics, between combinatorics and heat. It says that the arrow of time is in part an arrow of overwhelming numbers. This is why entropy is not just disorder as a vibe, even if the word invites that image. It is a count of possibilities consistent with what you know, given the constraints you impose. If you only know the macrostate, you do not know which microstate you're in. Thermal noise is the constant pressure toward that ignorance, and it is present wherever temperature is above absolute zero. At non-zero temperature, molecules jiggle and collide, exploring nearby microstates with relentless speed. The system naturally drifts toward macrostates that can be realized in more ways, because there are simply more routes that lead there. That drift is not a moral rule about neatness, and it is not a cosmic preference for mess. It is statistics plus dynamics, and it is why equilibrium is so common in the wild. Equilibrium is the macrostate with maximal compatible microstates given the constraints, the state that occupies almost all of the available phase space. If you could see phase space as a landscape, equilibrium would be the broad ocean, and low entropy states would be narrow coves. Systems do not choose the ocean, yet they fall into it because there are so many more ways to be there. The second law is less a commandment than a statement about typicality. Life is a long fight against that drift, and it wins only by spending. A living cell keeps gradients, membranes, and concentrations far from equilibrium, holding ions on one side and proteins in carefully folded shapes. It pays for that separation by consuming free energy and exporting entropy to the environment, usually as heat and waste products. The visuals here are microscopic and intimate. A membrane shimmering like a thin oil film, studded with pumps that open and close. Sodium and potassium ions move like beads in a current, and ATP molecules snap into ADP as chemical potential becomes work. The cell is not a static object. It is a controlled flow. Order is costly because it is fragile, and fragility has a thermodynamic meaning. To keep a specific pattern stable, you must constantly correct random perturbations that would otherwise accumulate. The correction requires energy, and the energy ends up as heat, because the environment absorbs the uncertainty you push away. This is where information becomes operational rather than poetic. If information is physical, then processing and erasing information must have physical costs, even when those costs are tiny. The clearest bridge is Landauer's principle, a result that ties logic to thermodynamics with unsettling elegance. Landauer's principle says erasing information has a minimum thermodynamic price, and it does not depend on the engineering details. To reset one bit to a standard value, you must dissipate at least kTln2 of heat into the environment. The cost is small per bit, but it is not optional because it is rooted in entropy accounting. Historically, this was a response to an older puzzle about Maxwell's demon, the imagined creature that sorts molecules and seems to cheat the second law. Landauer's insight was that the demon's memory must be reset, and that reset carries an entropy cost. When you include the bookkeeping, the second law survives, and the demon pays its bill. The key is what erasure means, because the word sounds like deletion from a notebook. Erasure is not moving a bit from one place to another, and it is not simply hiding it. Erasure is compressing many possible logical states into one fixed state, which dumps uncertainty into the environment as heat. You can compute reversibly in principle, without erasing intermediate results, and physicists have designed thought experiments that do exactly that. But most real computation uses resets, discards, and overwrites because they are practical and fast. Logical irreversibility forces thermodynamic irreversibility, and that is the core Landauer connection. Picture a tiny memory element as a ball in a double well potential, left for 0 and right for 1. Resetting it means forcing the ball into one well regardless of where it started, and that forcing must push entropy outward. The environment, in effect, becomes the trash bin for the alternatives you refuse to keep. This is not just about computers on desks humming in climate-controlled rooms. Brains are information processors embedded in warm, wet matter, and they operate near the edge of noise. They run on chemical energy, and much of that energy ultimately becomes heat, radiated away from the scalp and carried off by blood. Neurons maintain ion gradients that store potential differences, and those gradients are like charged springs held under tension. They spend ATP to pump sodium and potassium against diffusion, and they spend more to recycle neurotransmitters and repair molecular damage. The brain's power draw is modest in watts, but huge in informational consequence, because it is paying for stability. A useful comparison is a laptop that idles at a few tens of watts, yet can run a world of software. The brain runs on roughly the same order of power, but it must also build and maintain its own hardware while it computes. Every spike, every synaptic release, and every restored gradient is part of the thermodynamic budget. Every stable memory is a physical constraint, not a ghostly inscription floating above matter. Synapses must keep molecular states within ranges despite thermal agitation, molecular turnover, and chemical noise. That stability is maintained by ongoing metabolism, protein turnover, and cellular housekeeping that never truly pauses. So what does cessation imply in the plain language of mechanics and heat? When circulation stops, oxygen delivery collapses, and ATP production rapidly fails in energy-hungry tissue. The system stops paying the energetic rent that kept informational structures within usable bounds, and the protective routines begin to fall behind. The immediate result is not that information vanishes, as if a file were deleted from a drive. The immediate result is that information stops being curated, corrected, and refreshed. Patterns that were actively stabilized begin to drift, fragment, and thermalize because the barriers that held them in place are no longer maintained. Now we need a careful distinction that will matter later, because it separates physics from intuition. Physics often treats microscopic laws as reversible, yet everyday processes feel irreversible. Death feels like the most irreversible process of all, and our language reflects that finality. At the microscopic level, many fundamental equations are time-symmetric, at least to excellent approximation in ordinary conditions. If you reverse velocities in an idealized system, the equations allow the system to retrace its steps. Quantum evolution under Schrödinger's equation is unitary, which is reversible in principle, because it preserves inner products and total information. Macroscopic irreversibility comes from statistics and from entanglement with environments, and it arrives quickly. When a system interacts with many uncontrolled degrees of freedom, information spreads into correlations that are not tracked. The total information may be conserved, yet it becomes effectively unrecoverable, because no observer can gather and control the needed variables. This is the meaning of scrambling, and it is more than a metaphor. A message can be preserved in principle while being dispersed across so many variables that reconstruction becomes impossible in practice. The ledger still contains the entry, but it is written in microscopic ink scattered through the world. This is why the second law is not a claim that microinformation is destroyed, at least not in standard physics. It is a claim about typical behavior when you ignore most degrees of freedom, because you must. Coarse graining turns reversible microdynamics into irreversible macro trends, and the trends are what we live inside. A familiar example is mixing, and it looks almost magical in fast motion. Drop a dye into water and it spreads until the color looks uniform, as if the dye is dissolved into nothing. The molecular dynamics are reversible in principle, but reversing them would require controlling an astronomical number of positions and momenta, with precision beyond any realistic machine. The same logic applies to heat flow, which is mixing in energy space. A hot object cools in a room, and the room warms slightly, though you barely notice it. The microscopic state of the air contains the information about where the energy went, but retrieving it would require impossible coordination among countless molecules and photons. So we separate two meanings of lost, because the word hides a crucial fork. Information can be lost to us because we cannot access the correlations that contain it. Information can also be lost in principle if the fundamental dynamics truly deleted, which would violate unitarity and raise deep consistency problems. This distinction becomes sharp in quantum mechanics, where the mathematics forces you to be explicit. A closed quantum system evolves unitarily, which preserves the purity of the global state. But subsystems look mixed when entangled with environments, because we trace out what we cannot measure, and that partial view carries entropy. In that reduced description, coherence disappears and entropy increases, and the world looks classical. Yet the global state can still encode the correlations that would restore coherence if you could gather the environment and reverse the interaction. In practice, you cannot, because the environment is not a box but the rest of the universe. This is the bridge from Chapter 2's decoherence to Chapter 4's information, and it tightens the mystery rather than dissolving it. Decoherence is not annihilation of information, and it is not a collapse that erases history. Decoherence is the spread of phase information into the environment, where it becomes inaccessible to local observers. Now we bring this back to the central question, and we keep the terms disciplined. When a person dies, what happens to the information that constituted the person? We do not mean their story, but the physical pattern that implemented their memories, habits, and dispositions. The pattern that made one brain state lead to the next. To answer, we need an informational picture of the self that does not rely on a single hidden essence. The self is not a single file stored in one place, and it is not a solitary center you could point to. The self is a set of patterns distributed across multiple scales, maintained by ongoing dynamics that stitch moments into continuity. At the neural level, part of the pattern lives in synaptic weights, the strengths of connections shaped by experience. Synapses change strength through plasticity, and those strengths bias future activity in subtle ways. This is one substrate of memory, learning, and personality, and it is written into molecular arrangements that must be stabilized. Another part lives in connectome dynamics, not just static wiring, and this is easy to miss. Circuits reconfigure through neuromodulators, oscillations, and changing excitability, like a city whose streets stay put while traffic lights and rules constantly shift. The same anatomical network can implement different functional states across time, and that flexibility is part of identity. Another part lives in molecular states inside neurons and glia, where timescales stretch from seconds to months. Receptor densities, phosphorylation patterns, gene expression profiles, and structural proteins all contribute to how the network behaves. These are slow variables that shape long-term traits, and they are maintained by continual synthesis and degradation. The self, in this view, is a process rather than an object, and that phrasing is not just poetic. It is the ongoing stabilization and updating of a high-dimensional state, with feedback loops that correct drift. Identity is the persistence of a trajectory, not the persistence of a frozen snapshot, and trajectories require time, energy, and control. This matters because death interrupts process, and physics is blunt about what interruptions do. When the process stops, the pattern does not teleport elsewhere, and it does not remain protected by active correction. The pattern begins to decohere, diffuse, and degrade into other degrees of freedom, because the system is no longer steering itself. Some components persist briefly as structure, and the camera can linger on that uneasy stillness. Synaptic proteins and membrane architectures remain for a time, and the gross anatomy holds its shape, but without metabolism they are no longer repaired, and thermal motion plus chemistry begins to erase the fine distinctions that once mattered. Erasure here is not a deliberate reset, and that difference is important. It is the uncontrolled drift toward equilibrium, which effectively overwrites specific correlations by mixing them into the environment. The microstate still exists, but the macro-accessible pattern that supported cognition becomes unrecoverable, because the distinctions are no longer readable by any internal process. This is where Landau returns with a darker twist, because the same logic applies without any engineer present. The brain in life constantly performs controlled erasures and updates, paying heat costs while preserving function and preventing runaway noise. In death, the system undergoes uncontrolled erasure, where information is not efficiently compressed but chaotically dispersed, and the dispersal is indifferent to what we valued. The energy budget changes sign in a sense, and the imagery shifts from control to release. Instead of importing free energy to maintain low entropy structures, the body becomes a source of free energy for microbes and the environment. The remaining chemical potential is spent, and entropy production continues, now driven by decomposition and diffusion rather than homeostasis. From the ledger perspective, the entries do not stop, and the universe does not close the account. Heat flows outward, molecules react, and photons carry away energy and correlations into the surrounding air. The question becomes whether any of those correlations remain organized enough to count as a mind, or whether organization is precisely what is lost. Physics gives a strict answer about organization, even if it cannot satisfy the human question behind it. A mind requires integrated, recurrent information processing that is stable over time, with signals that can influence future signals in a coherent loop. When the biological machinery fails, the integrated processing ends, even if micro-information remains somewhere in the universe. This is the core tension we keep returning to, because it is where comfort and rigor diverge. Conservation does not imply recoverability, and it does not imply continuity of experience. The universe may conserve information in principle, while making it practically impossible to reconstruct the person from the scattered correlations. Now, we address reversibility with more precision, because it is often misunderstood in popular explanations. Reversibility is a property of the underlying equations for an isolated system, and it is a statement about what is allowed. Irreversibility is a property of typical macroscopic evolution, under coarse graining and environmental coupling, and it is a statement about what overwhelmingly happens. A living brain is not isolated, and it never was, even in the quietest room. It is open, driven, and constantly exchanging energy and matter with blood, air, and the rest of the body. Its apparent low entropy is maintained by exporting entropy to its surroundings, which increases the universe's total entropy overall, even as the brain stays functional. When the driving stops, the system relaxes, and relaxation has a specific physical meaning. Relaxation is the approach to equilibrium, and equilibrium corresponds to maximal entropy given constraints like total energy and particle number. The relaxation is effectively irreversible because the correlations that would reverse it are dispersed into the environment, and the environment does not keep them neatly labelled. This is why we can say two things at once without contradiction, even if they sound emotionally incompatible. The microdynamics can be reversible, and the macro outcome can be irreversible, because the mapping between them is many to one when you coarse grain. The ledger can be complete, and the record can still be unreadable, because readability is a local structured property. Now we tighten the language around information itself, because precision is part of the mood here. In classical terms, information is often measured in bits, and a bit is a choice between two distinguishable alternatives. In physical terms, bits correspond to distinguishable states of a system, like magnetization up or down, or a voltage high or low, separated by an energy barrier that resists noise. A bit is not abstract in the lab, and it is never free. It is a physical degree of freedom stabilized against thermal agitation, vibration, and electromagnetic interference. Stabilization requires energy barriers, error correction, redundancy, and time, all of which are thermodynamic commitments that show up as heat somewhere. Brains store bits in a different format than silicon, and the difference is part of their power and vulnerability. They store information in distributed analog and probabilistic patterns, where meaning is carried by populations rather than single switches. Yet the same physical logic applies, because any reliable distinction must be maintained against thermal fluctuations, and maintenance always has a cost. When the brain dies, it does not lose its atoms, and it does not vanish from the physical world. It loses its ability to keep distinction sharp because sharpness is work. The informational boundaries blur because the system stops doing the work required to keep them separated, and the environment does what environments do, it mixes. We can frame this as a shift in the brain's effective entropy, and the framing is not merely symbolic. The living brain maintains a low-entropy macrostate relative to equilibrium, with constrained microstates that support function and allow reliable signaling. Death releases constraints, expanding the accessible microstate set, and the expansion is the physical content of entropy increase. That expansion is what entropy increase means, and it can be said without mysticism. More microstates become compatible with the macroscopic description, because the macroscopic description becomes less specific as structure decays. The system becomes describable with fewer meaningful variables, because fewer variables remain controlled, and uncontrolled variables quickly become noise. Now we connect this to memory and identity with a sober claim that is easy to underestimate. Memories are not just stored, they are actively protected, and protection is a continuous activity. Sleep, synaptic homeostasis, glial cleanup, and molecular repair all contribute to keeping the memory substrate stable, and they do so by spending energy to keep errors from accumulating. When those processes stop, the memory substrate becomes vulnerable in ways that are both chemical and informational. Proteins denature, membranes leak, and chemical gradients flatten, changing the very parameters that once made signaling reliable. The pattern that once implemented a first-person model is no longer refreshed, and it degrades, first subtly and then catastrophically. This is not a metaphysical statement about the soul, and it does not pretend to answer every existential fear. It is a physical statement about what it takes to preserve a complex computational state in a noisy environment. Preservation requires energy, and death is the end of the energy supply that kept the computation running. Still, the ledger metaphor can mislead if we imagine a single book in a single place. In quantum physics, information is often stored in correlations, not in local properties, and correlations can be non-local. The universe's accounting is distributed, and it can be encoded in entanglement across many systems, which makes the record both complete and inaccessible. So we ask a sharper question, because the sharper question is where the mystery becomes clean. Could the information that constituted a person be preserved in principle, even if not accessible to any observer? Could the universe retain a complete microstate record that, in some extreme sense, still contains the person, even after the organized process has ended? In unitary quantum mechanics, the global wave function evolution preserves information, and that is the orthodox expectation. The correlations that once made up the brain state become correlations among the brain's remnants, the surrounding air, the emitted photons, and everything they later interact with. The record spreads outward like ripples, and each interaction writes a little more of it into the world. That is preservation in principle, but it is not survival in any ordinary sense, and the difference matters. A preserved correlation is not a preserved experience, because experience requires ongoing integration and update. A scrambled microstate is not a continuing point of view, because there is no mechanism left to read it as a self. To make that distinction concrete, imagine a book burned to ash, filmed in slow motion. The information in the ink and paper becomes information in smoke molecules, turbulent air, and heat photons that race away at light speed. In principle, a perfect daemon could reverse the process, but no physical agent we know can do it, because the required control is beyond reach. The self is more fragile than the book, because it is not a static inscription that can sit on a shelf. It is a running computation that depends on timing, feedback, and continuous energy input, and it must be robust against noise every second. When the computation halts, the experience halts, even if traces remain in matter and radiation. This is where the documentary tone stays mysterious without becoming vague, and the mystery is earned. Physics can describe the fate of information, but it cannot translate that fate into comfort, because comfort is not a physical variable. It can tell us what persists as correlations and what ends as organized process, and it can show us the gap between those categories. Now we prepare the next pivot, and we widen the lens without changing the subject. If information is physical, then the most extreme tests of information's fate occur where physics itself strains, and where our usual intuitions fail. The universe has boundaries where information seems to disappear behind horizons, and the bookkeeping becomes controversial. Black holes are the sharpest case, and they are the cleanest stage for the question. They are not just massive objects, they are regions with event horizons that limit what can be observed and what can influence the outside. If something crosses a horizon, its information appears to be lost to the outside world, not by destruction, but by inaccessibility. That appearance collides with quantum principles, and the collision has shaped modern theoretical physics for decades. If quantum evolution is unitary, information should not be destroyed, even in gravitational collapse. Yet Hawking's original calculations suggested black hole evaporation could turn pure states into thermal radiation, which looks like true information loss, not mere scrambling. We do not solve that paradox here, and we do not pretend the community has finished arguing about it, but we set it up as the next chapter's arena because it is the universe's hardest audit. The question of a person's informational traces becomes a subset of a larger cosmic question. Does the universe always preserve information, or can horizons erase it in principle? This transition matters for our central question about death, because it clarifies what kind of claim we are making. If the cosmos can delete information, then the ledger is not perfect, and the deepest conservation story fails. If the cosmos preserves information even across horizons, then death is not deletion, but dispersal into inaccessible correlations, and the tragedy is practical rather than fundamental. So we end this chapter with a controlled suspense, and with language that stays physical. The self as a living process ends, and the body's organized information becomes heat, chemistry, and scattered correlations that continue to interact with the world. The universe keeps writing, but the writing becomes unreadable at human scales, and that unreadability is its own kind of finality. Next, we follow information to the universe's most extreme bookkeeping problem. We go to black holes, horizons, and the edge of what it means for anything to be preserved, when even space and time begin to behave like a locked vault. We left the brain with a hard distinction, and it still hangs in the air like a verdict. The self ends as a process, while information becomes dispersed correlations that no longer feel like anyone. That split is clean on paper, yet the universe rarely grants clean endings, especially when gravity is allowed to close its fist. Now we test that ledger against the universe's most extreme accounting problem. We go where gravity builds a boundary that looks like forgetting, and where even light seems to misplace its future. In these regions, the question is not only what survives, but what can still be said to exist for an outside witness. A black hole begins as an ordinary story in general relativity, at least at first glance. Enough mass collapses, space-time curves, and escape becomes impossible, not because of force, but because geometry rewrites the available paths. The equations do not describe a vacuum that pulls harder. They describe a stage whose angles have been bent until out stops connecting to later. In the sky, the birth can look almost mundane. A massive star exhausts nuclear fuel, pressure support fails, and the core implodes while outer layers may explode as a supernova, an expanding shell lit by freshly forged elements. For a moment the scene is bright and violent, with shockwaves, neutrino floods, and heavy atoms flung into space like glittering ash. Einstein's equations allow this collapse, and Carl Schwarzschild wrote down the simplest black hole solution in 1916. It was a mathematical object at first, a strange curvature pattern on paper, long before telescopes could hint that nature actually uses it. Even Einstein doubted such objects would form, and for decades the idea hovered between calculation and disbelief. The defining feature is not the centre. The defining feature is the event horizon, a surface that separates what can reach infinity from what cannot, and it does so with the cold logic of causality. It is less like a wall and more like a one-way edge in the map of possible futures. From far away, the horizon is not a material wall you could scrape with a probe. It is a causal boundary, defined by light cones and the geometry of space-time, an invisible contour where outward stops being a viable direction. What changes is not your strength, but the set of routes that space-time allows light itself to take. Visually, imagine a grid painted onto space, then pulled downward like fabric into a deep funnel. Near the rim, paths still curve outward. Closer in, every arrow of possibility tilts toward the same interior destination. The closer you drift, the more the future looks like a slope, and the more every trajectory becomes a kind of surrender. Outside observers can still see the black hole's mass, charge, and spin. Those three numbers become the entire classical description, and everything else seems erased, a result summarized in the stark phrase, "no hair." The theorem is really a family of results, and it depends on assumptions like stationarity and classical fields, yet its message feels brutally universal. That phrase is not poetry, but it sounds like it. It means the messy details of the collapsing star, its chemical layers, magnetic knots, and asymmetric turbulence, do not remain visible as independent features once the horizon settles. The external gravitational field relaxes, as if the cosmos insists on a simplified receipt. In real astrophysical black holes, charge is usually negligible, because surrounding plasma neutralizes it quickly. Mass and spin remain, and spin matters enormously, twisting space-time itself through frame dragging, as if the hole were stirring the nearby vacuum. Around a rapidly spinning hole, even empty space acquires a kind of rotational preference and orbits precess as though the geometry has a current. Inside the horizon, trajectories point inward like time itself has tilted. Once crossed, every future-directed path leads deeper, regardless of engines or intentions, because future is now aligned with decreasing radius. In the mathematics, radius behaves like a time coordinate, and that swap is why escape is not merely difficult, it is undefined. This is one of the most unsettling parts to visualize. You can still point your rocket outward, you can still feel yourself accelerating, yet the geometry has already decided which destinations count as later moments. The horizon is not a trap that grabs you, it is a rule about what later can mean. To a distant observer, the approach to the horizon looks slow and strange. Light climbing out becomes increasingly redshifted, signals arrive later and later, and the infalling object appears to fade as if time were thickening into syrup. In practice, astrophysical environments complicate the view. Accretion disks blaze, jets lance outward, and the last photons are drowned in glare. To the infaller, the crossing can be unremarkable, at least for a large black hole. Locally, spacetime can look smooth, and the equivalence principle says free fall should feel like weightlessness. No special alarm at the boundary. For a supermassive hole, tidal forces at the horizon can be gentle, and the drama is delayed until deeper inside. The singularity sits at the center in the simplest solutions. It is where curvature diverges, and where our equations stop giving sensible answers, like a map that ends with a blank label reading, "Here be contradictions." In technical terms, geodesics become incomplete, and the theory cannot extend the story without new rules. Yet that breakdown is a signpost, not a destination. Singularities suggest general relativity is incomplete, and quantum gravity must replace the naive picture, just as quantum mechanics replaced classical orbits inside the atom. We learned, painfully, that nature does not tolerate infinities as literal objects. She uses them to tell us where our language fails. We have seen this pattern before in physics. When an equation predicts an infinity, it often means the theory is being pushed beyond its domain, and a deeper framework is waiting behind the curtain. The singularity is the loudest hint that spacetime itself may be quantized, or emergent, or both. Even without trusting the singularity, the horizon already creates a problem. It hides information from the outside, and it turns access into a one-way street, which is exactly the kind of setup that makes accounting ambiguous. A ledger is only meaningful if entries can, in principle, be reconciled. This is where the documentary's central question sharpens. If the universe keeps perfect accounts, can a horizon lock the ledger away forever, or does nature have a way to balance the books anyway? When causality draws a hard line, does physics accept the loss, or does it find a subtler route around the barrier? Classically, the answer looks simple, and it is brutally clean. Anything that falls in is gone to the outside world, except for those three conserved parameters, and the rest might as well have never existed. The horizon becomes a kind of cosmic shredder, not by grinding matter, but by denying access to its distinguishing marks. If you throw in an encyclopedia, a diamond, or a living brain, classical gravity does not care. From far away, the hole's external field settles into the same form, and the details vanish behind the causal curtain. The outside can still measure mass and spin with exquisite precision, yet it cannot read the story that produced them. But quantum physics refuses to let the story end there. Quantum fields fill space, even in vacuum, and they fluctuate everywhere, because empty in quantum theory is not nothing. It is the lowest energy state with restless uncertainty. Even when no particles are present, the fields retain jittery correlations, like a quiet room whose air never fully stops moving. In quantum field theory, particles are excitations of fields, and the vacuum contains correlations across space. Those correlations are subtle, but they are real, and they become crucial near horizons where different observers disagree about what counts as a particle. The disagreement is not about opinion, it is about how time is sliced, and time is part of the geometry. Near a horizon, those fluctuations meet curved space-time. The vacuum state for a distant observer is not the same as the vacuum for a falling observer, because time itself, used to define energy, depends on the observer's trajectory. In flat space, we can agree on a global clock, but near a black hole, the clock is local and contested. This observer dependence is not a loophole, it is the mechanism. In curved space-time, there is no single, universal notion of positive frequency, so no particles for one frame can translate into a thermal bath for another. The same field mode can be decomposed in different ways, and the decomposition determines what you call a particle. Hawking's insight was that horizons change what counts as empty. The horizon splits field modes into inside and outside, and entanglement spans the boundary, linking what escapes with what is trapped. The vacuum, when traced over inaccessible interior modes, looks like heat to the exterior. Historically, this arrived in the 1970s, when Stephen Hawking combined quantum field theory with classical curved spacetime. It was a shock because black holes had seemed like perfect absorbers, and perfect absorbers were supposed to be cold. Instead, the horizon behaved like a thermodynamic surface, with a temperature that could be written in a simple formula. A common explanation uses particle pairs, and it is useful if we treat it gently. A fluctuation produces two correlated excitations. One escapes outward, and one falls inward, like two notes from the same chord separated by a boundary. In the visuals, you can imagine twin ripples on a dark sea, one ripple carried outward by the tide, the other pulled under. The escaping part becomes Hawking radiation. The infalling partner carries negative energy relative to infinity, reducing the black hole's mass, so the hole slowly loses energy in order to pay for the outgoing flux. The horizon, once thought permanent, becomes a slowly leaking bank account. Negative energy sounds like fantasy, but it is a bookkeeping statement tied to curved space-time. Near the horizon, the definition of energy depends on the time-like killing vector used by distant observers, and the infalling mode can contribute with the opposite sign. In plain terms, the gravitational field lets the accounting be done in a way that would be impossible in ordinary flat space. The pair story is a guide, not literal billiard balls popping into existence. The deeper claim is that quantum field theory predicts radiation with a thermal spectrum, with a temperature set by surface gravity at the horizon. That temperature depends on mass and spin, and it is inversely related to mass for simple, non-rotating holes. That temperature is tiny for stellar mass black holes, far colder than the cosmic microwave background. For such holes, the universe actually feeds them more energy than they radiate. So evaporation is a principle more than an everyday astronomical event. Only in a far future colder cosmos would their slow glow dominate the balance. For small black holes, the temperature rises as mass falls, and the process accelerates. The mathematics implies a runaway finale, although the last stage is precisely where semi-classical approximations may fail. Another signpost toward quantum gravity. If a final burst exists, it would be a brief flare at the edge of our current understanding. Thermal means it looks like heat. It carries energy, but it seems to carry no detailed imprint of what formed the black hole, the way a warm brick does not remember the shape of the hand that touched it. The spectrum is smooth, and smoothness is the enemy of storytelling. In thermodynamics, heat is the great blender. It smooths differences into averages, and it replaces specific histories with macroscopic quantities like temperature, pressure, and entropy. That is why thermal radiation feels like forgetfulness made physical. Over immense times, the black hole evaporates. Small black holes evaporate quickly, large ones evaporate slowly, but the direction is the same, and the horizon's area shrinks as if the boundary itself were dissolving. The shrinkage is not merely geometric, it is tied to a decrease in entropy, which is already a provocative statement. If evaporation completes, the horizon disappears. What remains is a bath of radiation spread across space, apparently random and memoryless, thin photons and other quanta drifting through an ever-expanding cosmos. The final scene is quiet, with no central object left to point to, only a diluted afterglow. This is where tension becomes a paradox, and the paradox is sharp enough to cut theory. A pure quantum state seems to become a mixed thermal state, as if information is truly destroyed, not merely hidden behind a wall. The horizon looks like a one-way filter that turns precise inputs into generic outputs. In ordinary quantum mechanics, that is forbidden. Unitary evolution preserves information in the global wave function, even when subsystems look thermal, because apparent randomness can arise from entanglement rather than true erasure. The mathematics insist that the full state evolves reversibly, even when we cannot track the reversibility. A familiar example is a shuffled deck sealed in a box. To you it looks random, but the exact order still exists, and someone with the key could in principle recover it, because the evolution never deleted the arrangement. The box hides information, yet it does not annihilate it. So we face a fork that shaped modern theory. Either Hawking's calculation implies non-unitary physics, or our understanding of horizons is missing something, and the missing piece must be subtle enough to hide in plain sight. The fork is not optional, because both quantum theory and relativity are experimentally triumphant in their domains. The crisis is not philosophical decoration, it is a consistency check between quantum theory and gravity, and it threatens the idea of a perfect cosmic ledger, because the ledger is only meaningful if the rules never tear pages out. If information can vanish, then prediction becomes fundamentally limited, not just practically hard. The information paradox can be stated without mysticism, and without metaphors about souls. If you know the exact initial state, you should in principle predict the exact final state, at least in the limit of perfect measurement and perfect computation. A universe that forgets would be a universe where distinct paths can collapse into the same future. Thermal radiation seems to erase that predictability. Many different initial states would lead to the same featureless output, which is true deletion, the kind that would force quantum mechanics to be rewritten at its foundations. That is why the paradox mattered even to people who never cared about black holes as astronomical objects. Hawking originally argued information is lost. That would mean quantum mechanics is only approximate, and the universe sometimes forgets in principle, not because of ignorance, but because the laws themselves discard distinctions. It is difficult to overstate how radical that claim is, given how deeply unitarity is woven into modern physics. Others argued the opposite, sometimes with equal confidence. They claimed the radiation must contain subtle correlations, so the final state is pure even if it looks thermal locally, and the apparent loss is only a coarse-grained mirage. The challenge was to show where those correlations could hide without violating the causal structure that the horizon seems to enforce. The debate forced physicists to ask what information means in gravity. It also forced them to ask where information can be stored when spacetime itself is dynamical, and when the boundary between system and environment is a geometric surface. When geometry can fluctuate, the very definition of inside becomes part of the quantum problem. One clue came from black hole thermodynamics, developed by Bekenstein and others before Hawking's full result. A black hole has an entropy proportional to its horizon area, not its volume, and that single fact still feels like a coded message. The proportionality constant even contains Planck's constant, hinting that quantum mechanics is not optional here. Entropy counts microstates, the number of internal configurations consistent with what you can measure. Area scaling is strange because ordinary matter stores degrees of freedom throughout its bulk, yet black holes seem to compress their accounting onto a surface. It is as if nature has imposed a maximum information density, with the horizon acting like a limit. Bekenstein's reasoning began with a thought experiment about dropping entropy into a black hole. If entropy could disappear, the second law of thermodynamics would fail, so he proposed that black holes must carry entropy of their own, an entropy tied to horizon area. In that move, the horizon stopped being a mere boundary and became a thermodynamic object. Hawking's radiation then supplied the missing piece, temperature. With both temperature and entropy, black holes behave like thermodynamic objects, obeying laws that echo classical thermodynamics, but with geometry playing the role of state variable. The first law becomes a relation between changes in mass, area, and angular momentum, as if space-time itself were a working substance. That scaling suggests the number of internal states grows like a surface, as if the horizon is the relevant storage device. It invites a radical suspicion that the inside might not contain independent degrees of freedom beyond what the boundary already encodes. If that suspicion is right, then the paradox is not solved by hiding information deeper, but by redefining where deeper is. This leads to the holographic principle. The physics inside a region may be encoded on its boundary, with no loss of information, much as a hologram stores a three-dimensional image on a two-dimensional film. The principle is motivated by black holes, but it speaks more broadly about how gravity counts possible states. Holography is not a metaphor about projections, and it is not a claim that the world is fake. It is a claim about degrees of freedom and how gravity counts states, and it suggests that our usual intuition about volume and storage is misleading. When gravity is strong, the boundary can be the true register. The strongest evidence comes from ADCFT, proposed by Juan Maldacena in 1997. In certain spacetimes, a gravity theory in the bulk is equivalent to a quantum field theory on the boundary, and equivalent here means the same physics in different language. It is a duality that trades curved geometry for ordinary quantum dynamics without gravity, and the trade is exact in the models where it applies. In that duality, the boundary theory is manifestly unitary. If the duality is correct, black hole formation and evaporation in that setting cannot destroy information, because the boundary evolution never loses track of the quantum state. The black hole becomes a complicated, thermal-looking state in the boundary theory, but not a state that breaks the rules. This does not prove our universe is ADS, and it does not solve every detail of evaporation in our sky. It shows that quantum gravity can be unitary, and that horizons can be consistent with perfect bookkeeping, even when semi-classical reasoning says otherwise. It also suggests a philosophical shift. Perhaps space-time is not the primary container, but a derived description. If information is preserved, how does it escape? The answer must be in correlations within the Hawking radiation, not in its average thermal spectrum, because the average is too smooth to carry a detailed message. The message, if it exists, must be written in relationships between quanta, not in their individual faces. The radiation can look thermal in coarse measurements, yet fine-grained measurements across many quanta could reveal entanglement patterns that encode the past, like a watermark that appears only when you compare many pixels at once. The universe could be whispering the truth in cross-references, not in headlines. This idea introduces a new timescale. Early radiation can be almost thermal, while later radiation must carry increasing information to purify the total state, and the transition point becomes a diagnostic of whether unitarity survives. The black hole, in this view, behaves like a system that first hides information, then gradually returns it in a highly scrambled form. This is the Page curve story, named after Don Page. Entropy of the radiation rises, reaches a peak near the Page time, then falls if evolution is unitary, because the radiation eventually contains enough degrees of freedom to encode the black hole's microstate. The curve is a simple shape, yet it functions like a lie detector for theories of evaporation. Hawking's original semi-classical calculation predicts a different curve. It predicts entropy keeps rising, which signals true information loss, because the radiation never becomes sufficiently correlated to reconstruct a pure global state. The disagreement is not aesthetic. It is a measurable statement in principle, even if the measurements are fantastical. So the paradox becomes quantitative, not merely rhetorical. Which curve does quantum gravity produce, and what mechanism changes the semi-classical answer, given that the semi-classical method seems so well motivated? How can a calculation that respects local quantum field theory so carefully still miss the global bookkeeping? Several proposed resolutions try to keep both principles without rewriting physics too violently. One is black hole complementarity, which says no single observer sees a violation because the descriptions available to different observers cannot be combined into one global narrative. It is a rule about operational consistency, not about comforting stories. From outside, information is reflected or scrambled at the horizon, as if the horizon were a hot membrane that absorbs, thermalizes, and re-emits. From inside, the infaller sees nothing special at the horizon and carries information inward, consistent with local smoothness. The two accounts contradict if you try to merge them, yet complementarity claims no experiment can force that merger. Complementarity relies on a limit that is operational, not metaphysical. No observer can compare both stories, because doing so would require impossible communication across the horizon, and physics only demands consistency for what can actually be checked. The horizon becomes a boundary not only for travel, but for comparisons. But complementarity ran into a sharper challenge, and it arrived like a formal accusation. The AMEMP's argument suggested that preserving unitarity and smooth horizons might be incompatible, once you track entanglement carefully across early and late Hawking quanta. The paradox was no longer vague, it was written in inequalities about quantum correlations. This is the firewall controversy. If late radiation is entangled with early radiation to preserve purity, it cannot also be entangled with interior partners, and the naive pair creation picture near the horizon becomes a logical trap. The very mechanism that produced Hawking radiation now seemed to demand a violent correction. Quantum entanglement is monogamous. A system cannot be maximally entangled with two independent systems at once, and that simple rule, almost a bookkeeping constraint, turns into a crisis when you demand all the usual principles simultaneously. The horizon, once smooth by assumption, becomes the point where assumptions collide. If the entanglement structure must change, something gives. Either the horizon is not smooth, or unitarity fails, or locality breaks down, and each option carries a cost that reaches beyond black holes. The question becomes which principle is negotiable, and which is the bedrock. A firewall would mean high-energy quanta at the horizon, not a gentle vacuum. An infalling observer would be burned, contradicting the equivalence principle's promise of ordinary free fall and turning the horizon into a physical surface after all. The image is stark, an invisible boundary that suddenly behaves like a furnace. The community did not accept a single verdict, and the disagreement was productive. The firewall debate clarified the stakes, and it sharpened what any resolution must explain, especially how semi-classical physics can be so accurate and yet so misleading. It forced theorists to specify where, exactly, the standard picture must be amended. Then came progress that changed the mood, not by ending controversy, but by producing concrete calculations. New work in semi-classical gravity, using replica tricks and quantum extremal surfaces, produced the page curve in models where it had been missing. For the first time, the desired curve emerged from a controlled procedure rather than from hope. The replica method is a mathematical technique borrowed from statistical physics and quantum information. It computes entropies by considering multiple copies of a system, then analytically continuing a parameter, an abstract move that somehow reveals a very physical curve. The calculation feels like a magician's flourish, yet it is anchored in careful path integrals. The key concept is islands. Regions inside the black hole can be included in the entanglement wedge of the radiation, changing what counts as the radiation's entropy, and reshaping the boundary between accessible and included in the accounting. In the visuals, the island is a surprising patch of interior spacetime that the outside description must secretly include. This is technical, but the narrative core is simple. The naive separation between inside and outside was wrong for fine-grained quantum information, because gravity allows the bookkeeping region to be defined in a way that is not purely geometric in the classical sense. The entropy you compute depends on a quantum-corrected notion of what region you are really tracing over. With islands, the entropy of radiation can rise then fall. The result matches unitary expectations, at least in controlled models, and it suggests that semi-classical gravity, when corrected by the right quantum prescription, already contains the seeds of the cure. The horizon still matters, but it no longer guarantees permanent concealment. Islands suggest information is not lost. It is encoded in non-local correlations that semi-classical observers miss when they treat spacetime as a fixed background, and when they assume the horizon cleanly partitions the Hilbert space into two independent halves. The partition, it turns out, was an approximation that breaks precisely when the paradox becomes sharp. Non-local here does not mean faster-than-light messaging. It means the mapping between where information is and where you would point in space becomes subtle, because quantum gravity ties geometry to entanglement in ways that classical intuition does not anticipate. The ledger is still balanced, but the columns are not where you thought they were. This does not end the story, and no honest narration should pretend it does. The derivations rely on specific setups, and the interpretation still raises questions about what is real and what is bookkeeping, especially when we ask what an observer can actually measure. Are islands a literal region an observer could, even in principle, operationally identify, or are they a tool for computing what the theory demands? Some physicists see islands as strong evidence for unitarity, and they treat the page curve as a decisive signature. Others worry about assumptions, and about whether the mechanism is fully understood in our universe, where cosmology and realistic collapse add complications. The debate has shifted from whether the paradox is serious to which cure is the correct medicine. Still, the direction is clear, and it is not a small shift. The trend in modern theory favours information preservation, even when horizons make it look impossible, and that trend aligns with the deeper expectation that quantum mechanics does not tolerate true deletion. If the universe forgets, it would have to forget in a way that hides from every consistency check we know how to perform. That preservation comes with a price, and it is a price of intelligibility. The information is not preserved as a readable narrative, but as scrambled correlations distributed across radiation and fields, so that kept does not mean retrievable. The ledger may be complete, yet it may be written in ink that no human instrument can ever resolve. Scrambling is a technical term here, and it has a precise flavour. Black holes appear to be fast scramblers, mixing information across their degrees of freedom extremely efficiently, approaching the fastest rate allowed by quantum chaos bounds. In that sense, a black hole is not a safe, it is a blender that operates at the quantum limit. If you drop a message into a black hole, it is not simply stored like a file in a drawer. It is rapidly spread into subtle correlations, making retrieval extraordinarily difficult, because any local imprint is diluted into a global pattern. The message becomes a property of the whole, not of any part you can easily isolate. Even the word difficult is misleading because the difficulty scales brutally. To reconstruct the message, you would need access to an enormous fraction of the radiation and the ability to perform exquisitely precise collective measurements, operations far beyond any plausible technology. Theoretically allowed does not mean physically reachable, yet difficult is not the same as forbidden. The paradox forces us to separate practical loss from fundamental loss, the same distinction we used for death, where the end of a process is real even if microscopic traces remain. The difference matters because physics is ultimately about what the laws permit, not what our hands can do. Now we connect back to Chapter 4's ledger. A horizon is the universe's harshest test of whether information can be destroyed in principle, because it creates a region that is not merely far away, but causally disconnected. It is the cleanest place to ask whether the universe ever truly tears out pages. If black holes preserve information, the ledger is deeper than our access. The universe may keep accounts even when no observer can read them locally, and the balance may be maintained in correlations that look like noise to any limited viewpoint. The cosmos, in that case, is not merciful, it is merely consistent. But we must not smuggle comfort into that conclusion, because comfort is not a theorem. Unitary evolution does not imply personal consciousness continues, because consciousness is not just information storage, and it is not merely a pattern frozen in a static register. A pattern that is not running is not an experience. A mind is a running, integrated process, sustained by metabolism, signaling, and continual error correction. If the process stops, the first-person point of view stops, even if micro-information persists globally in the state of surrounding matter and radiation. The ledger can keep traces without keeping a witness. So what does black hole physics imply for a life, when we translate the abstraction back into human scale? It implies that physical traces may never be truly deleted, even when they are hopelessly scrambled, and even when no one can gather them into a coherent story again. It also asks a quieter question. What would it even mean to recover a life from correlations if the recovery is not the life? A person's actions radiate outward as photons, gravitational perturbations, and chemical changes. Those changes entangle with the world, and the world carries them forward, embedding tiny differences into air molecules, soil chemistry, and the thermal glow of everyday objects. In a dim room, even the infrared shimmer from skin and walls is part of the record, slipping away at light speed. In principle, the universe contains correlations that depend on those actions. In practice, the correlations disperse into degrees of freedom no one can recombine, because the environment acts like an amplifier that spreads information into untrackable channels. The record becomes everywhere, and therefore nowhere you can point to and say, here is the person. Black holes add a darker possibility, and it is darker because it is geometrically final. Some of those traces could fall behind horizons, apparently removed from the accessible universe for eons, while the outside continues as if the swallowed history had been amputated. The horizon makes forgetting look like a law, not merely a limitation. If information is preserved, those traces are not annihilated. They're encoded in the combined state of the black hole and its radiation, then in radiation alone, and the encoding is so scrambled that it resembles a cipher without a key. The universe may keep the ciphertext forever, while the plain text is gone as a lived reality. If information were truly destroyed, the implication would be profound, and not only for black holes. The universe would sometimes erase history, and the ledger would have missing pages, meaning that two different pasts could converge into one identical future. That kind of convergence would be a new principle, and it would rewrite what we mean by causality at the quantum level. Modern work suggests missing pages may be an illusion of limited perspective. The pages might be written in a code that looks like noise unless you hold the whole book, and unless you know the quantum gravitational rules for reading the margins. The horizon, then, is not a shredder, it is a lock, and the key is a theory we are still learning to speak. That is the mysterious lesson we keep, and it is not sentimental. The cosmos may not forget, but it does not remember in human form, and it does not preserve what we care about in the format we recognize as experience. It preserves correlations, not meaning, and it preserves structure, not the feeling of being alive. So we end this chapter with a controlled claim, not a promise. Quantum physics does not confirm an afterlife, yet it pushes against the idea of absolute erasure, and it forces us to be precise about what gone really means. When we say something is lost, do we mean inaccessible, unrecoverable, or absent from the laws themselves? The self as a living process ends at death. The physical record disperses into matter, radiation, and correlations that may persist, scrambled beyond recognition, like ink dissolved into an ocean where the molecules still carry the dye. The ocean keeps the chemistry, but it does not keep the sentence. Next, we widen the horizon again, and the word horizon will change its meaning. We move from black holes to the universe itself, where cosmic expansion creates new boundaries and new kinds of forgetting, and where the ledger is written across the largest scales we can imagine. The ledger metaphor has carried us from neurons to horizons, and it keeps asking the same question. When a mind goes dark, what changes in reality's accounting? What is conserved, what is scrambled, and what is truly gone? On screen, imagine a book of accounts floating in darkness, its pages turning without hands. The ink is not words but traces, faint interference fringes, thermal noise, and the ghostly afterimages of measurement records. In physics, the ledger is not moral bookkeeping, it is information in the technical sense, correlations between systems that can in principle be read. Yet the human question remains stubbornly personal. If the universe keeps records, does it also keep a witness? After black holes, the temptation is to reach for the strangest quantum refuge. Many worlds and quantum immortality promise a loophole that sounds like survival, written into the mathematics of measurement. The promise arrives with a particular aesthetic. Cold equations that seem to whisper comfort. But comfort is not evidence, and the mathematics is quieter than the stories we build around it. We have to slow down and separate three things that are often blended. There is the formalism, there are interpretations of that formalism, and there are predictions that experiments can actually test. That separation is not pedantry. It is the difference between physics and myth wearing physics as a mask. Quantum mechanics gives us a shared core, and that core is astonishingly strict. States evolve by Schrödinger's equation when isolated, and probabilities follow the Born rule when outcomes are recorded. Unitary evolution preserves total probability and, in a precise sense, preserves information in the full quantum state. That is why the ledger metaphor keeps returning. It is built into the mathematics. The dispute begins at measurement, where the clean unitary story meets the messy world of definite outcomes. Does the wave function physically collapse? Does it only update our knowledge, or does it never collapse at all? The equations can be written the same way, but the story we tell about what is real changes dramatically. Historically, this tension has been present since the early days of the theory. In the 1920s, quantum mechanics worked too well to ignore, yet it described nature in a language that resisted common sense. The founders argued in letters and lectures about what the symbols meant, not because they enjoyed philosophy, but because the symbols seemed to demand it. Start with a Copenhagen-like family of views because it is the cultural default. In these views, measurement is a special event where a definite outcome appears, and the wave function is treated as a tool for predicting those outcomes. The emphasis is pragmatic. Calculate what you will see, then stop. Visually, we might show a laboratory bench, a detector clicking, and a waveform on a screen snapping into a single spike. Some Copenhagen-like accounts treat collapse as fundamental but undefined, tied to measurement as a primitive. Others treat collapse as an effective rule for updating information, while the underlying reality is left deliberately quiet. That quietness is sometimes mistaken for mysticism, but is often just restraint. The view says, in effect, that the theory is a map for outcomes, not a photograph of what exists between them. Then there is many worlds, which makes a clean promise and a bold refusal. The wave function always evolves unitarily. There is no physical collapse, and measurement is just entanglement plus decoherence. The price is conceptual. You must accept that the universal state contains mutually non-interfering histories. If that sounds extravagant, remember that it is also conservative, because it adds no new dynamics. Finally, there are objective collapse models, which change the dynamics rather than the story. They add a real stochastic collapse process, often tuned to leave microscopic physics intact while suppressing macroscopic superpositions. In these models, the wave function is not merely updated, it is physically forced into definite outcomes. The universe, in a sense, edits its own ledger. GRW and CSL are the famous examples in this family. They predict tiny deviations from unitary evolution, and those deviations can be constrained by interferometry and precision experiments. The details matter. GRW introduces spontaneous localization events at a low rate per particle, while CSL spreads that idea into a continuous noise-driven process. Either way, the aim is the same: keep atoms quantum, keep cats classical. Here is the key discipline for this chapter, and it is easy to lose in the glow of speculation. Many interpretations share the same experimental predictions across ordinary laboratory regimes, so interpretation is not the same thing as a new testable claim. If two stories generate identical statistics for every experiment we can perform, then the difference is not empirical, at least for now. That is why quantum afterlife arguments often float in a grey zone. They borrow the authority of tested equations, then slide into metaphysical conclusions that the equations do not force. The slide is subtle because the language of quantum theory is already strange. When you hear superposition and observer, it is tempting to hear mind and spirit, even when the math says nothing of the kind. Now we explain many worlds in the least mystical way, with the camera lingering on ordinary objects. The universal wave function contains superpositions, and interactions entangle systems with measuring devices and environments. A photon hits a detector, a neuron fires, a pointer moves, and the quantum description becomes a web of correlations. Nothing supernatural happens, just more entanglement. Decoherence does the heavy lifting, and it is not a vague handwave. When a system becomes entangled with many uncontrolled degrees of freedom, phase relationships become inaccessible to local observers. In plain language, the delicate wave-like relationships between alternatives get smeared into the environment. The information is not destroyed, but it becomes effectively unrecoverable, without impossible control over countless particles. In that reduced description, interference between different outcomes disappears extremely fast. The world looks classical because the environment has copied outcome information into many places. A warm room is a relentless copying machine. Photons scatter, air molecules collide, and vibrations ripple through solids. Each interaction is a tiny act of record-making. Branching is a name for that loss of interference between histories. It is not a literal explosion of matter into parallel copies occupying the same space. If you want a visual, imagine a single beam of light passing through fog and splitting into many faint paths. The paths are not separate universes stacked like pages, they are patterns of correlation that stop overlapping. Nothing splits like a cell dividing, and no energy is created by branching. The global state remains one state, while local observers become correlated with different records. This is a crucial correction because popular accounts often picture a cosmic cloning event. Technically, what multiplies is the number of stable, non-interfering descriptions available to subsystems. This matters because popular accounts often imagine a cosmic multiplication of worlds as a physical event. In the technical story, the multiplication is in the structure of the wave function and its decohered sectors. The worlds are not new matter. They are effectively isolated narratives, each with its own consistent history. The isolation is practical, not metaphysical. Each branch contains a consistent record, and within a branch the observer experiences one outcome. The other outcomes remain present in the global state, but they cannot interfere with the observer's record. That inability is not a philosophical decree, it is a dynamical consequence of entanglement with the environment. The environment becomes a vast archive that prevents recombination. The environment is the silent author of this separation, and it is everywhere. Air molecules, photons, and thermal vibrations entangle with macroscopic states, making the branches effectively autonomous. Even in vacuum chambers, stray radiation and internal vibrations do the job. Decoherence times for macroscopic objects can be unimaginably short, far less than a blink. Many worlds is attractive because it keeps the equations simple. It refuses to add a collapse postulate, and it treats measurement as ordinary physics applied universally. The appeal is aesthetic as much as technical, one law for electrons, detectors, and observers alike. Yet simplicity in equations can mean complexity in ontology. Yet the simplicity comes with a cost that is easy to miss if you only listen to the slogan. If all outcomes occur, then probability needs a new foundation, because which outcome happens is no longer the right question. We still place bets, we still expect frequencies, and we still feel surprise. But what does surprise mean in a universe where every result exists somewhere? This is where the Born rule becomes a central wound. In standard practice, the squared amplitude gives probabilities, but in many worlds every outcome exists, so what does probability even mean? The rule works flawlessly in the lab, but its interpretation becomes delicate. Are we talking about subjective expectation, about typicality, or about a measure over branches? There are proposed derivations using decision theory, symmetry, and typicality arguments. They aim to show that rational agents should weight branches by amplitude squared. Some arguments lean on invariances in the formalism, others on how an agent should plan under self-locating uncertainty. The common goal is to recover the Born rule without adding it as an axiom. Critics reply that these arguments smuggle in what they claim to derive. They argue that a measure over branches is an extra postulate, even if it is dressed as rationality. The criticism is not that the derivations are silly, but that they may be circular. If you assume the structure that makes squared amplitude special, you should not be surprised when it returns. The measure problem is not a side issue for our topic. Quantum immortality depends on how you count or weight observer moments across branches. If you treat every branch as equal, you get one intuition. If you weight by amplitude squared, you get another. If you admit that a branch counting is ill-defined, the ground shifts again. Now we introduce the thought experiment that made many worlds famous in pop culture, and we do it with the grim clarity it deserves. Quantum suicide imagines a device that kills or spares an observer based on a quantum outcome. In the toy version, a spin measurement triggers a gun. One result clicks harmlessly, the other fires. The point is not engineering, it is logic. From the outside, half the branches contain a dead observer, and half contain a living observer, in the simplest model. From the inside, the observer only ever finds themselves alive. The camera might show two silent rooms side by side, one empty, one occupied, then dissolve into a single first-person viewpoint that continues. The seduction is immediate, because the viewpoint seems to select itself. Quantum immortality is the stronger claim drawn from that setup. It says the observer's subjective experience continues only along survival branches, so they never experience their own death. The claim feels like a loophole in mortality, created by the structure of branching. But the feeling is not the argument, and the argument is not the physics. We treat this as a thought experiment, not a prediction. It is a probe of how first-person experience might map onto branching structure if many worlds is taken literally. Thought experiments are valuable because they expose hidden assumptions. They are dangerous when they are mistaken for empirical guarantees. The argument relies on a seductive shift in perspective. It replaces what is typical in the multiverse with what I will experience, then assumes the I is guaranteed to persist. That last step is doing almost all the work, and it is rarely examined. If we are honest, it is the step that smuggles desire into the logic. But the I is exactly what needs analysis, and the problem predates quantum mechanics. Identity across time is already a hard problem in ordinary neuroscience. Even before branching multiplies the possible continuations, your brain changes every moment. Synapses strengthen, neurons fatigue, memories reconsolidate. Continuity is a biological achievement, not a metaphysical given. In our earlier chapters, the self was framed as a maintained process. It is a trajectory stabilized by metabolism, error correction, and integrated brain dynamics. The stability is real, but it is not absolute. It depends on oxygen, glucose, ionic gradients, and the constant work of cellular repair. When those supports fail, the process frays. In many worlds, there are many future trajectories that resemble you. The thought experiment assumes that one of those trajectories is the one you will be, as if continuity were a selector. Yet continuity is not a force in the equations, it is a description we apply after the fact. The universe does not label one continuation as the true you. That assumption is not part of quantum mechanics. Quantum mechanics gives amplitudes for histories, not a privileged thread of personal identity that must be followed. The formalism is indifferent to names and pronouns. It tracks correlations, not the specialness of a viewpoint. To make quantum immortality work, you need a rule that connects experience to branches. You need a rule that says which observer moments count as you, and how they are weighted. Without such a rule, the claim is incomplete, like a map without a scale. It gestures towards survival, but never specifies what survival means. One hidden assumption is that any non-zero amplitude is enough for guaranteed subjective survival. That treats existence as binary. Ignoring that measure can be vanishingly small. In practice, physics is full of non-zero amplitudes that are effectively irrelevant. A process with probability 10 or 50 is not impossible, but it is not a plan. Another assumption is that personal identity is perfectly preserved across violent discontinuities. It treats survival as a switch, not as a gradual erosion of cognition and agency. Yet brains do not fail like light bulbs, and they do not recover like magic. Survival can mean confusion, aphasia, paralysis, or a personality altered beyond recognition. A third assumption is that the observer's reference class is well defined. It assumes there is a clean set of you copies, rather than a continuum of similar brain states. In reality, similarity is graded, and the boundaries of the same person are fuzzy. If branching produces many near copies, which ones inherit your first-person claim? These problems are not philosophical decoration, and they are not optional. They determine whether the thought experiment implies anything like a real expectation, or only a narrative trick. If you change the weighting rule, the conclusion changes. If you change the identity criterion, the conclusion changes again. Now we add the first major critique, which is typicality under the Born rule. If branch weights matter, then almost all measure can lie in branches where you die. In that case, you, as a typical observer moment, should expect death, not immortality. The existence of rare survival branches does not rescue the expectation. Quantum immortality tries to evade typicality by privileging first-person selection. It says you only ever sample branches where you're conscious, so you condition on survival. That move resembles survivorship bias in statistics, where you study only the planes that returned. The missing data, the silent branches, are exactly what you need to count. The bias becomes stronger when you imagine repeated trials. After many lethal measurements, the total measure of survival branches can shrink exponentially, even if one branch remains. In a visual metaphor, the surviving thread becomes a hair-thin filament in a vast tapestry. The filament still exists, but it is not typical. So the thought experiment becomes a question about measure, not a promise about experience. Are you guaranteed to find yourself in the last surviving sliver, or are you overwhelmingly likely to end? The question sounds personal, but it is mathematical. It asks whether being you tracks existence or weight. Many worlds by itself does not answer that. It gives a branching structure and amplitudes, but it does not supply a unique rule for mapping amplitudes to first-person certainty. Some many worlds advocates argue that rational expectation follows the Born weights. Others argue that self-locating uncertainty changes the story. The disagreement is not cosmetic, it is foundational. Now we add the second critique, which is that death is not a single binary event. Real dying is often gradual, with partial loss of function, confusion, pain, and decline. The body can keep breathing while the cortex is failing, and the heart can beat while awareness is gone. Medicine has whole vocabularies for these borderlands. Quantum immortality stories usually assume a clean outcome. Either you are alive and intact, or you are dead and absent. That is a cinematic simplification, and it is understandable. But biology rarely offers that clarity, and the brain rarely offers that mercy. Biology offers branches where you survive with severe brain injury, branches where you survive with dementia, and branches where you survive while suffering. There are continuations where speech is lost, where memory fragments, where personality becomes unrecognizable. If survival means any flicker of consciousness, the story darkens. The loophole stops looking like salvation. If survival includes any continuation of consciousness, then the thought experiment can imply not rescue but prolonged deterioration. The narrative flips from comforting to grim, and it flips for physical reasons. The brain is not a single module that is either on or off. It is a network with many failure modes. This is not a rhetorical trick. It is a point about what counts as the observer. If the observer is a brain process, then many continuations are degraded processes. A continuation can be conscious but trapped, aware but unable to act, or awake inside a collapsing cognitive landscape. Would that count as immortality, or as a kind of endless harm? Now we add the third critique, which is about what Many Worlds actually says about minds. Many Worlds is a claim about universal quantum states, not a theory of consciousness. It tells you how amplitudes evolve, not how experience arises. To connect it to experience, you must assume a philosophy of mind. You must decide whether consciousness supervenes on classical brain states, on quantum states, or on something else. Our earlier chapters emphasize decoherence in warm, wet brains. Whatever quantum degrees of freedom exist, they are rapidly entangled with the environment and become effectively classical for neural computation. The brain is noisy, thermal, and chemically active. Conditions that crush delicate quantum coherence. That matters because quantum immortality is often sold as quantum consciousness escaping death. Many Worlds does not imply any protected quantum soul-like substrate in the brain. It does not provide a hidden qubit where the self is stored. It treats the brain as matter obeying the same dynamics as everything else. In Many Worlds, the brain is still a physical system that fails when oxygen and ATP fail. Branching does not prevent the breakdown of integrated function that ends awareness. Neurons maintain voltage gradients with energy, and synapses depend on precise chemical cycles. When circulation stops, the gradients collapse, and the network loses the ability to sustain coherent cognition. Now we address a common misunderstanding directly, because it is the engine of many popular claims. People sometimes imagine that Many Worlds guarantees a branch where you wake up after any lethal event. They picture a cosmic safety net that always catches you. But the existence of a branch is not the same as a reasonable expectation of being in it. If its measure is astronomically small, it is not a robust prediction about your future. In everyday terms, it is like saying you will win a lottery because someone must win. Someone does, but that does not make your ticket special. Many Worlds does not crown a single viewpoint as the beneficiary of improbability. Even worse, the branch where you survive might require improbable physics. It might involve unlikely medical miracles, unlikely coincidences, or unlikely error chains in biology. A bullet misfires, a tumour spontaneously regresses, a heart restarts after minutes without damage. Such events are not forbidden, but they are weighted accordingly. Many Worlds allows low-amplitude histories, but it does not elevate them to destiny. It treats them as part of the global superposition, weighted by amplitude. The ledger contains them, but it does not recommend them. If you confuse exists somewhere with will happen to me, you have changed the meaning of probability. Now we clarify what objective collapse models would say, because they change the thought experiment's premise. If collapse is real and stochastic, then there may be only one outcome, not many. In that case, quantum immortality loses its mechanism. You cannot rely on branching survival if the dynamic selects a single history. Objective collapse models also bring the discussion closer to experiment, which is where physics earns its authority. They predict specific deviations from standard quantum statistics, and those deviations are constrained by data. Experiments with massive molecules, optomechanical resonators, and ultra-sensitive noise measurements all squeeze the parameter space. The absence of observed collapse-like effects does not prove Many Worlds, but it limits alternatives. So the afterlife implications depend on which interpretation is true, and we do not know which is true. That uncertainty is part of the honest mystery, not a gap to fill with wishful certainty. The universe does not owe us consolation, and physics does not owe us metaphysics. It owes us predictions that survive contact with measurement. Now we return to Copenhagen-like views, because they are often used to smuggle in consciousness. Some popular accounts claim the observer's mind collapses the wave function. The idea is culturally sticky, partly because the word observer sounds psychological. But in modern physics, an observer can be a photodiode, a bubble chamber, or a memory register. We have already separated measurement from awareness. In modern physics, measurement is physical record formation, and decoherence explains why records become stable. A record is a durable correlation, an imprint that can be copied and checked. Consciousness may read records, but it is not required to make them. So even if collapse exists, it need not be caused by consciousness. And if collapse is only an update rule, it tells us nothing about survival after death. The wave function would be a computational device, not a spirit meter. Either way, the leap to an afterlife is not licensed by the theory. The deeper point is that interpretations are not free metaphysics. They are constrained by the same experiments, and they must reproduce the same operational predictions. You cannot declare an interpretation true because it feels meaningful. You have to show where it differs, and how the difference could be tested. When people say quantum physics proves an afterlife, they usually confuse interpretation with prediction. They treat a speculative story about measurement as a direct statement about death. The confusion is understandable because quantum language is slippery, but the correction is simple. Equations do not automatically translate into existential guarantees. Now we tighten the chapter's claim, and we do it without dismissing the fascination. Many worlds is a coherent interpretation, and quantum immortality is a provocative thought experiment within it. But quantum immortality is not an established consequence of quantum theory. It depends on contested assumptions about identity, measure, and the mapping from physics to experience. We can still learn from it, because it forces a clean question. What would it mean for a first-person perspective to persist if the universe contains many future continuations? Is persistence a matter of there being at least one continuation, or a matter of being typical among them? And what does typical mean when the observer is part of the system being counted? The answer is not in the equations alone. It sits at the intersection of quantum foundations, probability, and neuroscience's account of what a self actually is. The self is not a particle with a world line, it is an organized pattern that depends on ongoing physical support. That is a hard truth, and it is also a clarifying one. Now we connect back to the documentary's central question in a sharper way. The universe may keep perfect accounts of information, yet that does not guarantee a continuing witness. Information can persist as correlations long after the process that cared about them has ended. A photograph remains when the subject is gone. Many worlds, if true, makes the ledger vast. It says every outcome is recorded somewhere in the global state, and decoherence makes those records locally irreversible. Irreversible here means practically irreversible. Recovering coherence would require controlling the environment with absurd precision. The past becomes fixed not by magic, but by entanglement spread. But the ledger's completeness is not the same as personal continuation. A record of you is not you experiencing, and a branch where you survive is not a promise you will. The difference is subtle until you feel it. A diary can describe a life perfectly, yet it does not contain the living point of view. This is where the contemplative tone earns its restraint. The mystery is not that physics hides an afterlife, it is that physics is silent about the part we most want. It tells us what happens to amplitudes, to energy, to entropy, to correlations. It does not tell us why there is something it is like to be a brain at all. Now we transition to grounded terrain, because death is not primarily a quantum measurement problem. Empirically, dying is the breakdown of integrated brain function. Whatever interpretation you prefer, the clinical arc is the same. Circulation fails, oxygen drops, metabolism collapses, and the brain's coordinated activity fragments. When oxygen delivery fails, neural signaling fragments, and the global workspace that binds perception and memory collapses. You can watch this in physiology. Electrical rhythms degrade, connectivity patterns change, and responsiveness disappears. The details vary, but the direction is consistent. Awareness depends on integration, and integration is fragile. Whatever interpretation you prefer, that functional collapse is what we can measure. We can measure oxygen saturation, carbon dioxide, blood pressure, and the electrical signatures of cortical activity. We can correlate those measures with reports from people who return. The ledger here is not cosmic, it is clinical. So the next step is not to chase more exotic branches. The next step is to examine near-death experiences and what they reveal about brains under extreme stress. If tunnels and lights appear, what circuitry can generate them? If life reviews occur, what memory systems are being disinhibited? If peace arrives, what neurochemistry might be responsible? We move from speculative cosmology of selves to clinical phenomenology of dying minds. The question becomes how vivid experience can arise as the brain destabilizes and what that implies about consciousness. The camera can shift from abstract wave functions to hospital monitors, EKG lines, EEG traces, and oxygen readouts pulsing in dim light. The mystery does not shrink, but it becomes testable. The ledger remains in the background, still keeping accounts. But the story returns to the only place we can directly sample experience, inside the living brain, at the edge of its failure. If there is a lesson in quantum immortality, it may be humility. The universe can be vast and indifferent, and still leave us with the intimate question of what it means to end. In the next chapter, we follow reports of tunnels, lights, and life reviews into the physiology that can generate them. We ask what the brain is doing when it's close to stopping, and what that teaches us about what stops. They describe a tunnel that narrows into brightness, then opens into impossible calm, as if geometry itself becomes a corridor. They describe floating above the bed, high near the ceiling, watching clinicians work with practiced urgency under harsh white light. They describe hearing words later confirmed, clipped phrases and numbers that seem to arrive from outside ordinary hearing. They describe a life review that arrives as a compressed panorama, vivid and emotionally precise, like a library opened all at once. They describe meeting presences, crossing thresholds, then returning with grief and certainty. Certainty not about facts, but about felt meaning. Near-death experiences are reported across ages, cultures, and medical contexts, often with striking similarities that invite both awe and scrutiny. The reports are sincere, and the impact can be lifelong, reshaping fear, values, and identity in ways families and clinicians often recognize. The question is not whether people experience these events, because they do, and the testimonies are consistent in their intensity. The question is what brain states can generate perceptions that feel more real than waking life, even when the body is failing. We have to slow down and separate three things that are often blended. There is the subjective report, there is the physiological crisis, and there is the external timeline that clinicians try to reconstruct. The report can be honest, detailed, and transformative, while still being internally constructed by a nervous system under strain. The crisis can be measurable, while still leaving gaps in what we can record at the bedside. The timeline can be reconstructed, while still being uncertain at the minute-by-minute level, especially when alarms, drugs, and chaos compress time. This chapter is the climax because it touches the closest thing to a first-person dataset about dying, gathered from people who returned. It is where mystery and measurement collide in the same room, one side speaking in metaphors, the other in waveforms and blood gases. It is where the ledger metaphor becomes intimate, because experience itself seems to flare when the system is near collapse. If the universe keeps accounts, why does the mind sometimes produce a final, coherent story, as if it is balancing its own books? We begin with the common features, because they map to known neural functions and known failure modes. The tunnel is a visual geometry, often paired with a central light that seems both distant and intimate. The detachment is a change in body ownership and self-location, as if the eye is unhooked from muscle and skin. The life review is memory access plus emotional tagging at unusual speed, with a sense of moral clarity that can feel external. The peace is effective modulation under extreme stress, sometimes arriving after terror like a sudden weather front. Immediately we ask the core question in clinical terms, because poetry is not a mechanism. What patterns of oxygen, carbon dioxide, neurotransmitters, and network disinhibition can produce these perceptions in a human brain? What circuits can generate out-of-body perspective without leaving the skull, while still feeling spatially literal? What mechanisms can compress time and expand meaning without requiring external verification, even when attention is fragmented? What failure modes of the brain can feel like transcendence, and why do they carry such conviction? Physiology at the brink starts with circulation and gas exchange, the ordinary logistics that keep neurons working. When blood flow drops, oxygen delivery falls, and carbon dioxide rises, and those changes propagate through every synapse. Hypoxia and hypercapnia change neuronal excitability and vascular tone, and they do it unevenly across regions. They alter pH, ion channel behavior, and synaptic release probabilities, which is a technical way of saying they change what signals can travel. They can produce confusion, euphoria, panic, and vivid imagery, sometimes in rapid succession like a flickering film. Hypoxia is not a single switch that turns consciousness off. and that misconception matters for how we interpret stories. It is a gradient that destabilizes networks in stages, with different regions failing at different times depending on metabolism and blood supply. The cortex can lose fine integration while deeper arousal systems still drive fragments of experience, like a theatre with power in the lobby but failing lights on stage. That mismatch can feel like separation, because the usual binding of body, world and narrative is disrupted. The brain can be disorganized and still generate intense, coherent seeming scenes, because coherence is also a construction. Hypercapnia adds its own signature, and it often arrives alongside hypoxia in respiratory failure or poor perfusion. Rising CO2 can produce air hunger, pressure sensations, and altered time perception, because chemoreceptors in the brainstem and carotid bodies treat it as an emergency. It can also increase cerebral blood flow transiently, changing the balance of excitation and inhibition in ways that vary by person. In some contexts, it produces dreamlike states and panic. In others, it produces calm detachment that patients later describe as letting go. The same chemical stress can yield different phenomenology depending on prior state and context, including fear, sedation, and expectation. As oxygen falls, inhibitory interneurons can fail before excitatory neurons fully shut down, and that ordering is crucial. That creates cortical disinhibition, a brief window where activity becomes noisy and unconstrained, like a city grid losing traffic lights. Disinhibition can amplify internally generated imagery and spontaneous associations because the brain's usual gating is weakened. It can also create a sense of clarity because competing signals are no longer regulated normally and one narrative dominates. The brain's filters loosen and the world can feel flooded with significance, even when sensory input is degraded. Stress chemistry arrives fast, and it arrives with evolutionary purpose. Catecholamines surge, shaping attention and memory encoding under threat by narrowing focus and increasing signal gain. Cortisol rises, altering hippocampal function and retrieval dynamics, which can both impair and distort memory, while also stamping it with salience. Endogenous opioids can blunt pain and create warmth or peace, a biochemical mercy that can be misread as external comfort. These are not spiritual explanations, but they are powerful levers on subjective reality, and they can change the emotional color of a scene within seconds. Some researchers point to serotonin and glutamate shifts under extreme stress, because these systems tune perception, mood, and the sense of self. Others focus on NMDA receptor dynamics and dissociation-like states, especially when the brain is flooded with stress hormones and inflammatory signals. The details vary across cases, and we should not pretend there is one universal cocktail that fits every story. The key point is that neurochemistry can change the felt texture of consciousness within seconds, even without any new external information. A mind can move from terror to serenity without any external change, because the internal control knobs are being turned. There is also the simple fact of sensory deprivation layered onto crisis. As perfusion drops, hearing and vision do not fail cleanly, and the remaining input can be fragmentary and misleading. The brain hates gaps, and it fills them with predictions, memories, and plausible continuations of the scene. That filling in is not a flaw unique to dying brains, because it happens in normal perception every day. Under extreme conditions, the balance shifts, and prediction can overwhelm input, making inner imagery feel like outer reality. Now, we transition to grounded terrain, because death is not primarily a quantum measurement problem. In hospitals, the edge of death is monitored with imperfect tools, used by teams who must act before certainty arrives. We have ECG for cardiac rhythm, pulse oximetry for oxygenation, and sometimes EEG for cortical electrical activity, each with its own lag and vulnerability. Each tool samples a slice of the system, and each has blind spots that are easy to forget in hindsight. The absence of a signal is not always the absence of activity, and the presence of a signal is not always evidence of awareness. The clinical scene itself shapes what can be remembered. The room is often loud with alarms, ventilator hiss, and hurried speech, while the patient's body is still and sometimes paralyzed by medication. Resuscitation involves compressions, shocks, airway maneuvers, and drugs that change circulation and brain chemistry in real time. Even when a person later reports calm, the body may have been in violent motion from chest compressions. That mismatch between inner stillness and outer urgency is part of what makes the narrative so uncanny. EEG is central to NDE debates, and it is often misunderstood even by educated audiences. Scalp EEG measures summed postsynaptic potentials, filtered through skull and tissue, which means it is a coarse proxy for coordinated cortical activity. It is insensitive to deep structures, and it can miss localized or transient activity that might still support experience. During cardiac arrest, EEG often becomes isoelectric within tens of seconds, but recording conditions are rarely ideal in emergencies. Artifacts, timing uncertainty, and sparse sampling limit strong conclusions, especially when electrodes shift or electrical noise contaminates the trace. It also matters what isoelectric means in practice. A flat-looking scalp EEG can coexist with residual activity in deeper networks, and it can miss small islands of cortical activation that do not synchronize broadly. Consciousness, if it occurs, may not require the same large-scale rhythms we associate with normal wakefulness. That is not a claim that awareness persists during arrest, but it is a reminder about measurement limits. When we interpret an absence, we must ask what exactly was measured and what was invisible. Some studies report bursts of high-frequency activity near the time of cardiac arrest in animals and in limited human observations, and those findings are often oversold. These bursts can reflect terminal spreading depolarization, seizure-like activity, or stress-driven network events that occur as gradients collapse. They do not prove organized consciousness, but they show that the dying brain is not always a simple fade to black. The last moments can include complex dynamics that are easy to misinterpret, especially when we want a clean boundary. Terminal spreading depolarization itself is a dramatic phenomenon with a plain language meaning. As energy fails, neurons cannot maintain their ionic separation, and a wave of depolarization travels across cortex like a slow electrical storm. That wave can silence normal signaling, but it can also produce transient patterns that resemble activation. In some clinical contexts, patients with severe brain injury show a final loss of electrical activity that is not instantaneous. The brain, even at the end, can move through stages rather than a single switch off. The key limitation is temporal alignment, and it haunts every attempt at interpretation. An NDE report is narrated after recovery, often hours or days later, when the person is safe and the mind is rebuilding. The physiological crisis unfolds in seconds to minutes, often with sedation, hypothermia, or resuscitation drugs that alter memory formation. The memory may not map cleanly onto the moment of lowest perfusion, because the brain may not encode during the deepest trough. A vivid narrative can be stitched from fragments before, during, and after the worst point, and the stitch can be invisible to the storyteller. Anesthesia awareness is an important bridge case, because it shows how outward unresponsiveness can hide inner experience. People under general anesthesia can sometimes form memories, feel pain, or hear speech, despite appearing unresponsive and later being assumed unconscious. This shows that outward signs can underestimate inner experience, especially when paralysis prevents movement. It also shows that memory formation can occur in altered states that later feel surreal or hyperreal, with a strange clarity. NDE-like elements can appear without any claim about leaving the body, which keeps the focus on mechanisms. Historically, near-death narratives have been recorded for centuries, even when the language was theological rather than neurological. In medieval Europe, visions at the brink were often interpreted as moral instruction, and the life review became a story of judgment. In other cultures, the threshold might be a river, a gate, or an ancestral village, and the return might be framed as a mission. The continuity across eras suggests a shared human brain, while the differences reveal the power of local symbols. When the mind reaches for a map, it often chooses the map it already knows. Now we move from physiology to mechanisms that mimic NDE features, because similarity can be informative without being dismissive. Out-of-body experiences are strongly linked to the temporoparietal junction, a hub where the brain integrates multisensory signals. The TPJ integrates vestibular signals, proprioception, and visual perspective into a coherent body model that usually feels effortless. Disruption of this integration can shift self-location and produce a third-person viewpoint, sometimes with a sense of hovering. Electrical stimulation and lesions can trigger OB-like sensations in controlled settings, which is rare evidence in a field full of anecdotes. This matters because the OB is often treated as the strongest evidence for separation, the one feature that seems to demand a literal exit. Yet neuroscience can reproduce the core feature by perturbing multisensory integration without any metaphysical claim. The mind can feel located above the body, while the body remains the only physical substrate, because location is an inference. The experience is real as experience, even if it is not a literal displacement in space. The brain's body model is a prediction constrained by signals, not a direct readout of reality. Virtual reality experiments make this point vivid in a way words struggle to match. When vision and touch are manipulated in synchrony, people can feel ownership over a rubber hand or even a whole avatar body. With the right cues, the self can drift, and the felt center can relocate. These effects are not identical to NDEs, but they show how flexible embodiment can be. If embodiment is a model, then crisis can scramble the model, and the result can feel like flight. The tunnel and light can be approached through visual system physiology, including both the eye and the cortex. Under hypoxia, peripheral vision can degrade before central vision, creating a narrowing field that resembles looking down a tube. Retinal and cortical changes can produce phosphonares, bright spots, and geometric patterns, especially when inhibitory control is weakened. Migraine aura and seizure phenomena show how the brain can generate luminous forms without external light, including zigzags and expanding rings. A tunnel is a plausible perceptual artifact under constrained input and altered gain control, made cinematic by the mind's narrative engine. The light itself is often described as intelligent or welcoming, which raises a question about effect. Under stress, the brain's salience networks can assign overwhelming importance to a simple percept, especially when it arrives with relief from pain or fear. A bright central percept can become a symbol of safety, because safety is what the system is desperate to find. The visual cortex provides the raw sensation, while limbic systems provide the meaning. In that coupling, a glare can become a presence. REM intrusion is another major candidate mechanism, and it connects NDEs to the architecture of sleep. REM sleep features vivid imagery, emotional intensity, and muscle atonia, and it is governed by brainstem circuits that can sometimes misfire. If REM-like processes intrude into waking states, hallucinations and paralysis can occur, often with a terrifying sense of being pinned. Sleep paralysis often includes presences, pressure sensations, and fear or awe, because threat detection remains active while movement is blocked. Under stress, the boundary between REM and wake can blur, and the mind can slip into dream logic while still oriented to the room. Some NDE features resemble REM phenomenology, and the resemblance is not superficial. The vividness, the narrative flow, and the sense of encountering agents can resemble dream cognition, where the brain generates characters with apparent autonomy. The brain can generate social presence through predictive models when sensory input is ambiguous, and those models are tuned by attachment and fear. In crisis, prediction can dominate perception, because the system is starved of reliable data and must guess. The result can feel like contact with something beyond the self, even when it is the self modeling itself. Dissociation provides another route, and it is well studied in both trauma and pharmacology. Ketamine, an NMDA antagonist, can produce depersonalization, derealization, and out-of-body sensations, often with a sense of floating through spaces. It can also produce tunnels, lights, and encounters with entities, with a peculiar mixture of fear and fascination. The similarity does not mean NDEs are ketamine states, but it shows a mechanistic pathway through disrupted integration. Altered glutamatergic signaling can decouple self-model from sensory anchoring, leaving a mind that feels unmoored. Endorphins and other neuromodulators can reshape time, which is why the instant life review can feel both fast and vast. Under threat, time can dilate or compress, and memory can be encoded with unusual salience, as if the brain stamps it with a hot iron. The locus coeruleus and noradrenergic systems can amplify select details while suppressing others, creating a spotlight effect. That can create a sense of crispness, as if the moment is outside ordinary time and physics. The brain's clock is not a single metronome, but a distributed inference built from attention, prediction, and bodily signals. The life review is often described as instantaneous and morally charged, and it is tempting to treat it as supernatural accounting. Memory science suggests that under stress, associative networks can activate broadly, especially when inhibitory control is weakened. The hippocampus and medial temporal structures can release fragments, while prefrontal control is altered, reducing the usual editorial filter. The result can be a rapid cascade of autobiographical scenes, linked by emotion rather than chronology. The moral tone can reflect limbic tagging and social cognition, not external judgment, because the brain is saturated with the question of what mattered. It is also worth noticing what a review accomplishes psychologically. When a person is near death, the self faces a possible end, and the mind may attempt a final integration of identity. The review can function like a compression algorithm, reducing a lifetime into themes and turning points. That compression can feel like revelation because it reveals patterns the person never articulated. Is it any wonder that it changes people when it frames life as a single, interpretable object? Temporal lobe activity is frequently implicated in spiritual and mystical experiences, and the literature here is long and often contentious. Seizures and stimulation in temporal regions can produce déjà vu, presence, and intense meaning, sometimes accompanied by auditory or visual phenomena. This does not reduce the experience to pathology, but it anchors it in circuitry that assigns significance. Meaning is a brain function, and it can be amplified dramatically when networks destabilize. At the edge of failure, meaning can surge even as accuracy declines, which is a painful trade. We should address the hardest cases with care, because they are the ones that keep the debate alive. Some people report veridical perceptions during periods of apparent unconsciousness, including details about staff actions or objects in the room. These reports deserve investigation, not dismissal, because they are testable in principle and morally important to patients. Yet they face methodological obstacles, including timing uncertainty, reconstruction, and the simple fact that hospitals are information-rich environments. A correct detail can be learned before or after the crisis, then misattributed to the peak event, especially when the narrative is later smoothed. Prospective studies have attempted hidden targets in resuscitation areas, placing images or symbols out of normal sight lines to test the above-the-body claim. Results so far do not provide strong evidence of perception from an external vantage, and the null results are themselves informative. The absence of evidence is not proof of impossibility, but it sets a baseline for what has been observed under controlled attempts. Extraordinary claims require tight protocols and clear timestamps, because memory is slippery under trauma. Without them, the ledger of events is too smudged to audit, and interpretation becomes a mirror. Now we pivot to memory and narrative, because this is where NDEs become coherent stories that can be told and retold. Traumatic events fragment attention and disrupt normal encoding, because the brain prioritizes survival signals over orderly recording. Later, the brain reconstructs a timeline using inference, emotion, and available cues, including what others said happened. Reconstruction is not lying, it is how memory works, and it is how identity remains continuous. A sincere witness can deliver a polished narrative that was assembled after the fact, with confidence that feels like truth. Confabulation is a loaded word, so we use it carefully and with respect for the experiencer. In clinical confabulation, people fill gaps with invented details without awareness, often after brain injury. NDE narratives are not necessarily that, but they can share a principle of gap-filling under uncertainty. The brain prefers coherence over uncertainty, especially when the event threatens identity and existential security. A story that explains survival can stabilize the self, and stabilization can feel like revelation. Memory reconsolidation adds another layer, and it is one reason stories become more structured over time. Each retelling reopens the memory trace and allows modification, sometimes subtle and sometimes dramatic. Social feedback, therapy, and cultural scripts can shape what is emphasized, what is softened, and what is given symbolic weight. Over time, the narrative can become more organized and resonant, with clearer beginnings and endings. The person is not fabricating, but the memory is evolving, and evolution can increase conviction. Cultural expectations shape imagery in measurable ways, and this is where universality and diversity coexist. The core motifs recur, but the details often match religious and social context, including the language used to describe light, judgment, or welcome. Some see angels, some see ancestors, some see abstract light, some see bureaucratic thresholds, and some see nothing but vast quiet. The brain builds with available symbols when generating meaning, because symbols are the mind's native currency. A universal neurobiology can produce a family resemblance, while culture supplies the costume, the architecture and the names. Even the life review can be culturally inflected. In societies with strong moral bookkeeping, the review may feel like evaluation, while in other contexts it may feel like reconciliation or belonging. The emotional core can be similar, but the framing differs, and framing changes what people carry back. This does not cheapen the experience because meaning is always contextual. It simply reminds us that the mind speaks in the dialect it already knows. This is the ethical center of the chapter, and it requires a careful voice. We can honor the experience without treating it as a measurement of external reality, because compassion does not require credulity. We can validate the transformation without endorsing a specific metaphysical conclusion, because people change for real reasons. Sincere testimony is evidence of experience, not automatic evidence of an afterlife, and that distinction matters. The distinction protects both compassion and rigor, and it keeps science from becoming either cold or gullible. We connect this back to the documentary's central question, which has always been about what persists and what can be known. The universe keeps perfect accounts of energy and information, but it does not promise that accounts are readable by minds like ours. NDEs may be the brain's last coherent fireworks, a final burst of integration, as systems destabilize and constraints loosen. They may be what it feels like when prediction, memory and emotion run without normal boundaries, producing a story that feels complete. The ledger contains the traces, but the witness is still a biological process, and biology has limits. Quantum physics enters here only as a discipline against sloppy claims, not as a magic key. Warm, wet brains decohere quickly, and no NDE feature requires long-lived quantum coherence to be explained. The mechanisms we have described are classical neurobiology built on quantum chemistry, like all biology, from synaptic vesicles to receptor binding. If someone claims quantum entanglement explains tunnels and lights, they must specify a bridge mechanism and a test that could fail. Without that, quantum language is decoration, and decoration is not evidence. Still, the ledger metaphor remains useful, because it frames both the beauty and the distortion. During crisis, the brain is writing records under extreme noise, then rewriting them in recovery, and each rewrite can feel like discovery. The result can feel like a message from beyond, because it is a message from the boundary conditions of the self, what the system does when it's cornered. The boundary is not a horizon in space-time, but a threshold in physiology, where oxygen, pH, and network stability decide what can be experienced. The mind meets the limits of its own model of reality, and it does so with astonishing creativity. We do not end by shrinking the mystery into a diagnosis, because reduction is not the same as understanding. Even if every feature can be mapped to circuitry, the subjective intensity remains astonishing, and it demands humility. The fact that matter can generate a world of meaning at the edge of collapse is itself a mystery worth holding, even for strict materialists. The brain can produce love, terror, and transcendence with no external stage, and it can do so while its resources are failing. That is not an argument for an afterlife, but it is a reminder of what consciousness is and how fragile it can be. Now we connect back to Chapter 4's ledger. Information can persist as correlations even when a process ends, and physics is relentless about bookkeeping. NDEs show how the brain can generate a coherent narrative while information is being lost locally through hypoxia and disintegration, which is a paradox only if we expect neatness. The story can be vivid even as the substrate is failing, because vividness is not the same as accuracy. The mind can feel most alive when it is closest to stopping, and that observation should unsettle us. This sets up the final chapter's turn, and it sharpens the stakes. If NDEs are the last organized patterns before the lights go out, what remains after the lights go out, when there is no narrator? What does cosmology say about the fate of matter, energy, and information traces across deep time, when stars die and structures disperse? What does quantum physics allow us to claim about persistence without a persisting witness, and what does it forbid us to romanticize? The ledger continues, but does anything like a self continue, or is the self only a temporary accounting device? We end with a controlled tension, because certainty would be dishonest. Near-death experiences may be the brain's edge phenomena, not a window into another realm, and the mechanisms are increasingly legible, yet they show that the boundary between life and death is not a clean cut in experience, at least not from the inside. The last moments can be structured, meaningful and strange, like a final attempt to render a world from failing inputs. The void is approached through a mind that is still trying to make sense, and that effort is part of what we are. Next, we widen the horizon again, and the word horizon will change its meaning. We move from the brain's threshold to the universe's boundaries, where expansion and entropy decide what can be remembered and what becomes unreachable. We ask what the cosmos keeps, what it erases in practice, and what it never truly deletes, even when it becomes scrambled beyond recovery. The final audit begins. The universe keeps perfect accounts of energy and information, so we return to the ledger. In the mind's last quiet moment, what changes in reality's accounting and what does not? We have to slow down and separate three things that are often blended. There is consciousness as a living process, there are physical traces, and there are stories we wish physics implied. Those categories overlap in our emotions, yet nature treats them as distinct entries. Quantum physics underwrites chemistry, biology, and every neural signal we ever measured. Ion channels, neurotransmitter binding, and the electrical pulses of axons all depend on quantum rules, even when the brain behaves classically at our scale. Yet no confirmed mechanism in quantum theory implies personal consciousness survives bodily death. Interpretations still differ about collapse, branching, and what counts as a record. The Copenhagen tradition speaks in measurements, many worlds speaks in decohering branches, and other views shift the language without changing predictions. None of them, as tested today, provides evidence for a continuing first-person witness. It helps to remember how this question entered modern physics in the first place. Early quantum pioneers argued over observation and reality, and later popular culture folded observer into mind, as if they were the same. In laboratories, however, an observer is any system that irreversibly records outcomes, often a photodiode, a screen, or a cloud of scattered air molecules. Now we transition to grounded terrain, because death is not primarily a quantum measurement problem. Clinically and biologically, death is the end of organized brain dynamics that sustain awareness. The brain is not a static object. It is a constantly powered pattern, held together by metabolism and feedback. When oxygen and metabolism fail, gradients collapse and coordinated signaling breaks apart. ATP production falls, membrane potentials drift, and synapses lose the precise timing that makes perception and memory cohere. The pattern that was a mind stops being maintained, then becomes noise. Physics is strict about what remains. Mass and energy are conserved, and they change form and location. Nothing in known law allows a special self-substance to slip out of the balance sheet. Heat leaves the body through radiation, convection, and conduction into air and surfaces. In infrared, the body's warmth glows invisibly, like a fading ember seen by a thermal camera. Chemical energy becomes thermal motion, then disperses into the environment. Biochemical decay continues as microbes and enzymes dismantle complex molecules. Proteins unfold, membranes break, and long chains are cut into smaller fragments that diffuse and react. Order becomes simpler compounds, then becomes a broader distribution of states. Atoms do not vanish, and they do not keep identity labels. Carbon, nitrogen, oxygen, and calcium rejoin Earth's cycles through soil, water, and living networks. The same carbon that once sat in a neuron's membrane can later become leaf tissue, ocean carbonate, or a molecule in another animal's breath. Over long time, those atoms can be buried, recycled, and lifted again. Some will enter oceans, some will enter plants, and some will drift into rock. The planet's chemistry is a slow circulation, turning bodies into geology, and geology back into bodies. Eventually, geology and astrophysics take over the accounting. Plate tectonics, erosion, and atmospheric escape move matter, and the solar system itself is not permanent. Even the continents under our feet are temporary arrangements, sliding and folding on million-year clocks. The sun will brighten, then expand, and Earth's surface will be remade. Long before the red giant phase, increased luminosity will stress oceans and climate, pushing the biosphere toward limits. Far later, the solar system's debris can be scattered, captured, or ejected into interstellar space. The ledger also includes radiation that leaves immediately. Photons from body heat stream outward at light speed, carrying faint diluted records of a moment. They scatter off walls, leak through windows, and then spill into the night sky, thinning into near impossibility as distance grows. Gravity also carries influence outward, not as a message with meaning, but as changing curvature. Every motion slightly reshapes the gravitational field, then propagates away. The effect is unimaginably small, yet it is part of the same accounting that makes stars orbit and galaxies rotate. This is where the word information becomes slippery again. In physics, information means correlations in microstates, not memories with narrative content. A fingerprint on glass is information, and so is a thermal ripple in air, even when no mind can read it. In principle, unitary quantum evolution suggests microscopic correlations are not destroyed. Decoherence spreads them into the environment, making phases inaccessible to local observers. The world looks classical because those delicate relationships are dispersed into countless entangled degrees of freedom. But the living mind was a high-level pattern, stabilized by energy and error correction. Neurons constantly repair, regulate, and rebalance themselves, and the brain's networks suppress noise by spending metabolic fuel. Once the stabilizing work stops, the pattern is disrupted and thermally scrambled. Reconstruction is physically implausible, even if correlations persist somewhere. It is like unmixing smoke from the sky, requiring control over uncountable degrees of freedom. The barrier is not only ignorance, it is the practical impossibility of reversing a vast, entangled cascade. Black holes taught the same lesson with harsher geometry. Information may be preserved in correlations, yet horizons and scrambling can make recovery operationally impossible. The modern information paradox debate sharpened our language. Preserved in principle does not mean retrievable in practice. Cosmology adds another kind of horizon, created by expansion. Distant regions can become causally unreachable, so records can exist without any future observer accessing them. The universe can keep books that no one will ever open again. The far future depends on parameters we measure, and theories still incomplete. Stars burn out, galaxies thin, and usable free energy declines as entropy increases. The night sky, once crowded with burning furnaces, trends toward darkness punctuated by rare, fading embers. In a heat-death picture, complexity becomes harder to sustain. The ledger still holds correlations, but the universe offers fewer gradients to power new observers. Without temperature differences to exploit, even computation becomes expensive, and memory becomes fragile. Other scenarios remain possible, including vacuum decay or cyclic models. None currently restores personal continuity, and none is confirmed as a cosmic rescue. The sober point remains: physics describes transformations, not exemptions. So what remains is subtle and unsentimental. The self as an organized process likely ends when the brain's organized dynamics cease. What we call me appears to be an activity, dependent on structure, energy flow, and time. What remains is matter redistributed, energy degraded into heat, photons and gravitational ripples expanding outward. What remains is correlations embedded in an evolving cosmic record. The universe does not forget in the way a mind forgets, yet it also does not remember in the way a person remembers. The mystery becomes not a loophole but a horizon of inquiry. Physics can track conservation and scrambling, yet it cannot turn traces into a surviving person. And we can ask, quietly, whether meaning requires permanence or whether it can live fully inside finitude. We end where we began, with the ledger and its limits. Nothing simply vanishes, but not everything that persists is a life. The difference between a warm trace and an aware witness is the difference between residue and experience. The boundary between life and death remains existentially profound, even when mechanisms are clear. The resolution is the journey itself, learning how reality behaves at depth. In that learning, we trade comforting certainty for a sharper, stranger kind of awe. We are stardust organized briefly into questions, then return to the wider accounting. Meaning is not guaranteed by the cosmos, yet we can make it anyway. Our values are local creations, but they are not therefore unreal. For a moment, the universe is awake to its own laws through us. Then the lights go out and the ledger keeps turning. We began at a flat line, where medicine draws a practical boundary, and physics draws a different one, between substance that persists and organization that fails. From superposition and entanglement to decoherence and quantum Darwinism, we saw how measurement is record-making in matter, not a miracle performed by minds. In the brain, quantum rules are everywhere in chemistry. Yet the evidence still points to consciousness as a fragile, energy-funded pattern. One that unravels when oxygen, ATP, and coordinated signaling collapse. Information, in the physicist's sense, can be conserved and still become useless, dispersed into correlations too fine-grained to gather back into a story. Black holes pushed that idea to its limit, where horizons hide records, hawking radiation seems to bleach them away, and modern tools like page curves and islands suggest the ledger may balance without giving anyone the key. Many worlds and collapse theories reminded us that the deepest bookkeeping is still interpretive, and that no interpretation automatically grants a continuing witness. Near-death experiences showed how meaning can flare as the brain destabilizes, while the cosmos quietly keeps expanding, cooling, and diluting every trace into a long goodbye. So the journey ties into one hard-earned picture. Death ends a self the way a fire ends, not by erasing matter, but by losing the organized burn. The universe keeps everything that can be kept by its laws, yet it does not promise that what is kept remains accessible, or that it remains you. What we can say, without romance and without nihilism, is that physics treats your life as a real rearrangement of the world, one that leaves fingerprints even when the hand is gone. What we cannot honestly claim is a tested bridge from those fingerprints back to a first-person point of view, or a mechanism by which awareness survives the breakdown of its biological engine. Across every chapter, one question kept returning in new clothing: what is truly lost and what is merely transformed? Energy becomes heat and radiation, atoms rejoin the planet and the air, and the gravitational and electromagnetic ripples of your existence keep moving outward, fading but not vanishing. Yet the thing you called I was never a conserved quantity like charge. It was a maintained integration, an active error correction against noise, paid for moment by moment with free energy. When that payment stops, the brain's internal model stops updating, the global workspace stops broadcasting, and the coherence you need for a single, unified scene of experience fractures into local, decoupled chemistry. Quantum mechanics sharpens this rather than softening it, because it distinguishes between information as meaning and information as correlation. Unitary evolution suggests correlations are not simply deleted, but decoherence spreads them into the environment so quickly that the phases that made them usable become, for all practical purposes, gone. That is the central twist of the universe never forgets idea. The record can persist as an unimaginably distributed entanglement pattern, while still being as unreachable as smoke reforming into a candle. Then gravity enters, and the metaphor of memory becomes even stranger. A horizon is not a wall, it is a bookkeeping boundary, a limit on what can influence what, and therefore on what can ever be verified. Black holes taught us that even if information is preserved in principle, it may be preserved in a way no observer can operationally reconstruct, and the island story hints that what is real may depend on which description keeps the accounting consistent. Cosmological horizons repeat the lesson at the larger scale. The universe can be perfectly lawful and still become practically forgetful, simply because expansion and entropy make retrieval impossible. So where does that leave the quantum afterlife? The seductive claim that because information cannot be destroyed, the self must continue somewhere. It leaves it where good science often leaves our deepest hopes, with constraints, not consolations. If a self persists, it would require a demonstrable bridge mechanism, a way for quantum resources to survive warm, wet neural conditions, to shape spikes and synapses on cognitive timescales, and to remain integrated after the body's gradients fail. We do not have that evidence, and without it, quantum becomes a costume for belief, not a tool for understanding. And yet, the documentary's mystery does not evaporate. It simply changes its shape. The measurement problem remains open at the interpretive level. Many worlds still wrestles with what it means to count and observe a moment, and objective collapse models still face experiments that could, in time, rule them out or force us to revise the ledger itself. The far future is also unsettled because heat death, vacuum decay, and cycles are not just endings. They are different answers to how long any record can remain readable. Our uncertainty is not a failure of the story, it is the honest edge of what the story can currently be. In the end, the strongest claim quantum physics and cosmology offer is also the most sobering. You do not disappear, but you do end. The world retains the components and the consequences, while the particular integration that made them a viewpoint, a narrator, a felt interior, stops being maintained. What remains is not a hidden theatre where you continue watching, but a universe subtly altered by having once contained your patterns, your heat, your photons, your choices, and the cascades they triggered. This brings us back to the opening hook, the universe never forgets. So where does your consciousness go, and what exactly changes when you die? The reframed answer is that the universe keeps the accounting of physical influence, but it does not preserve personal experience as a conserved object, and it may keep even its correlations in forms no one can ever read. The ledger may be complete in principle, while the story of a self is complete in time. If there is a final gift in that, it is a kind of clarity. Meaning does not have to be guaranteed by permanence. It can be generated by a finite process that knows it is finite, and still chooses to be awake within it. In a cosmos where nothing simply vanishes, the most precious thing may be the brief interval when matter organizes itself into someone who can ask where it goes. So keep asking, but ask in ways the universe can answer, with better experiments, cleaner definitions, and the humility to separate what we measure from what we wish. Because the mystery is not a door marked afterlife, it is a horizon, inviting us to learn what can be known and to live wisely inside what cannot. If this journey changed how you think about death, share it, support the science that tests these ideas, and let the questions make your living more deliberate. The universe may never forget in the sense that physical influences and correlations are not simply erased, but that is not the same as consciousness continuing as a witness. When you die, the accounting changes through dispersal and scrambling, while the organized process that felt like you stops being sustained. Nothing simply vanishes, yet not everything can be gathered back, and the self is the kind of pattern that ends when its energy runs out. Mystery, then, is not an answer we inherit. It is an invitation to keep learning how reality keeps its books. If you want to push this frontier forward, follow the evidence, support careful neuroscience and fundamental physics research, and keep demanding questions that can be tested.